Good afternoon to everybody, and welcome in Scuola Normale. You will know more about Scuola Normale later in the day, because after, maybe just before the aperitif, we will have a small exhibition where we'll explain to you what Scuola Normale is and a bit of its story, and it will happen in the room here nearby. Today we have, in addition to three very nice lectures of the school, we have a keynote talk by a professor of the Scuola Normale, a biologist, who will tell us how we write in our brain, and we thought this was an argument that could interest more people than only biologists. So, since we are late, after my welcome, I will pass to Alberto that will chair the session.
Okay, so we will resume the lectures now, a different topic, hadronic physics. Michelangelo will describe the hadronic physics potential of new collider. So let's start.
Thank you, and welcome everybody to this beautiful room. So how many of you work, because yesterday we assessed you are all experimentalists, how many work in LHeC experiments? How many work on, say, B factory? Neutrinos? Heavy ions? What else? What have I left out? Antimatter. Dark matter, antimatter. Okay. So, let's see if I can get this to work. Yes. Can we have a whole screen dedicated to the slides? Yeah. So when we're talking about hadron colliders, future hadron colliders, we refer, first of all, of course, to the upgrade of the LHeC, the high luminosity LHeC. That's a project that is already approved. It will increase by a factor of, say, 10 to 20 the integrated luminosity relative to what is available today or what will be available soon. I will not cover the physics of high luminosity, because in a sense we really want to look at, I mean, for us in the context of this school, future really means beyond the LHeC and beyond any of the LHeC upgrades. So the real future hadron colliders are things that do not exist as yet, that have not been approved, and that we are simply discussing at this stage. On the CERN side, they rely on the so-called FCC that was introduced this morning in the context of E plus E minus collision. So it's a 100-kilometer tunnel that, aside from the plus E minus program that you heard about this morning, will eventually host a proton-proton collider at 100 TeV. So it's a factor of 7 increase in energy with respect to the LHC. In alternative, but as part of the same project from the point of view of the technology development, the 16 Tesla magnets that are required to get 100 TeV could in principle be used to upgrade the energy of the LHC, and that is a project that's called high energy LHC. So it would be 27 TeV in the 27-kilometer tunnel. Now, 16, you see, going from the LHC to the 100-kilometer tunnel is a factor of 4 increase in size, while the energy goes from 14 to 100, which is a factor of 7. So there is a factor of 2 in between, going from 4 to 7. The factor of 2 is in the magnets, because the magnets will have to have a magnetic field twice as large. And the rule of thumb, once you have a 16 Tesla magnet, which is what we're talking about, and perhaps Frank in the next lecture will discuss a bit, 16 Tesla means 1 TeV per kilometer. Okay, so that's 27 TeV in the LHC 27-kilometer tunnel, 100 TeV in the 100-kilometer FCC tunnel. Furthermore, it's possible to also have electron-proton collisions in the FCC, not using electrons from the electron beam used for E plus E minus collisions, but it's independent facility that would have to be built on purpose. A very similar, almost a photocopy of these is envisaged for the CEPC project, which again was introduced in the context of the plus and minus collisions this morning. There it's still 100 kilometers, but the energy that's been discussed for proton-proton collisions is 70 TeV as opposed to 100 because they have a slightly less ambitious but perhaps more realistic and more financially viable approach to the technology of a magnet. So those would be 12 Tesla magnets as opposed to 16 Tesla, but of course nothing prevents them from using more powerful magnets. So this is what we will be discussing, and I will focus on projections of physics performance based on the studies done in the context of the FCC. So yesterday I made a list of the three points, the three criteria that I suggested as a way of judging future facilities. One is the guaranteed deliverable, something that you get independently of the possible discoveries that you'll be making, and the guaranteed deliverables, of course, here would be the study of the Higgs and, of course, also the top quark, because the top quark, although he's been known for a long time compared to the Higgs, still it's a rather mysterious object. So it's a study of the Higgs and the exploration of Electroweak symmetry breaking phenomena with a precision and sensitivity which are well beyond anything we have today with the LHeC. So that is the guaranteed deliverable, and I will show you how that matches somehow what it can actually deliver. The exploration potential, we build a new machine to make discoveries. So even though we have no guaranteed discovery, still we want to make sure that we do cover a large fraction of possible BSM space. So the mass reach should be increased, and with 100 TeV, we increase it by a factor of 100 divided by 14. So it's a factor of, technically it's a factor of 7, but then there are issues like the parton luminosities evolving with Q square, so that at very high energy they drop a bit faster. So typically it's a factor of 5, the increase in the mass reach at the frontier, at the highest end. But the statistics is enhanced by several orders of magnitude for many BSM phenomena, but the LHeC could, for example, just barely touch in the course of its exploration. So it's not just the fact that we increase the mass reach by a factor of 5, but it's the fact that if the LHeC were to see some glimpse of possible new physics, by going up with energy in factor of 7, we would increase by hundreds or thousands the statistics, and therefore would be able to use this future machine to explore in deep detail what it is that the LHeC has discovered. And furthermore, we would benefit both, aside from the direct search for new particles, from an increased in precision, and again we will see in practice what this means. Having a much more precise machine experiments will allow us to again gain in sensitivity, especially for what concerns these elusive modes that are hard to detect. And finally, I mentioned as a third criterion the ability to provide conclusive yes or no answers to some very important questions. For example, is the standard model dynamics all that there is of a TeV scale? Is there a TeV scale solution to the hierarchy problem? Is dark matter a thermal WIMP? Either we discover it as a WIMP, or if we don't see anything, it means that dark matter is not a WIMP. It has to be something else, and then we forget about WIMPs. Was the cosmological Electroweak phase transition of first order, etc. So let me start from the guaranteed deliverable, so the things that absolutely the machine can provide, and we start with the Higgs properties. You've seen this morning what can be done with the plus and minus collider for what concerns the Higgs, and I will show you why. In addition to that, we would also need a PP collider at 100 TeV. And we start by looking at the rates, the number of Higgs that will be produced at 100 TeV in the lifetime of a machine. If we start from the most frequent production mode, which is glue goes to H, we are talking about 25 billion Higgses. So it's 10 times, more than 10,000 times more than a plus and minus. Of course, the environment here is much dirtier than in the plus minus, but unavoidably there are circumstances in which even in PP collisions we can actually see a specific decay of a Higgs. So all of a program of finding rare Higgs decays clearly requires this type of statistics. That is an increase of a factor of 200, that N100 over N14 is the number of events through the lifetime of 100 TV experiments divided by the number of Higgses produced during the whole lifetime of the LHeC, all the way up to the end of high luminosity phase. So you see gains going from 100, 200 up to 500 in the case of TTH and Higgs. So by just naively taking a square root of a number of events as a sense of how much the precision will improve, we're talking about a factor of 10 improvement, which is what we need to go from a few percent down to the sub-percent level precision. Now, what is unique of the FCCHH? That's the code name for the 100 TV machine. So as we just showed, huge Higgs production rates, they allow to access very rare decay modes, they push to the sub-percent level, in the case of a Higgs self-coupling, we get down to the few percent level, something that the high luminosity LHeC cannot do, something that the plus and minus cannot do. And as we will see, there are new opportunities to reduce systematic uncertainties, both theoretical and experimental, and push the precision also for the more bread and butter decay modes of the Higgs. There is a new element that enters in the 100 TV program compared to the LHeC program, and that is the huge dynamic range in Higgs production, namely the ability to produce Higgses at very, very high energy, very, very high PT. And what that does, it provides new regions where we can go and do Higgs physics with a new set of systematic uncertainties, both theoretical and experimental, and in particular regions where we can really push down those systematics to the percent level or below. There is a different hierarchy of the production processes. We'll see that in the next slide. And we can also develop an indirect sensitivity to BSM effects in Higgs physics that only show up or are enhanced as we go to very high Q square. And then, of course, there is the high energy reach. If there is a BSM Higgs sector, Higgses of large mass, other additional Higgses, here we have all of the energy required to find them. So this slide shows the rates. These are number of events on the y-axis corresponding to the production of Higgses with a PT larger than a given PT threshold. So 1 TV, 2 TV, 5 TV, produced in the 30 inverse attobars. That is the integrated luminosity of a machine. The different lines correspond to the different production modes, GLU-2H, TT, Higgs associated production, vector boson fusion, and in this case, associated production with a W. And one of the things that you notice is that while at low PT, which is the region where the LHeC typically does Higgs physics, as you see, the blue line is far bigger than anything else. In other words, GG, gluon-gluon fusion, is the dominant process. As we go to higher PTs, say in the range of 1 TeV, you see that TTH becomes more important. So if we have a Higgs at 1.5 TeV, it's more likely to come from associated production with the top than to have come from glue-glue fusion. And that, of course, changes completely the way in which we do analysis. A lot of analysis aim at trying to, separate all of the different contributions. If we want to pull out TT Higgs, we had to play special cuts to remove the GG Higgs background, etc. Here, somehow, by going to higher PT, we can select separate processes. This is also one other example of what happens when we go to very high PT. So this is one of the cleanest, possibly one of the cleanest ways to detect a Higgs, which is the Higgs decay into 2 photons. There is a very sharp mass peak. So in the background is 2 photons produced in a generic QCD process. But we require the 2 photons to be within, say, a couple of GeV, 4 GeV in this plot from the mass of a Higgs. So if we focus again on the low PT region, which is where most of the LHC data are from, you see the signal is the solid line, is a good factor of 30 below the backgrounds. And 1 to 30 is in fact the signal to background ratio at the LHC and remains pretty much the same, also at 100 TeV. But as we go to higher and higher PT, you see that the signal becomes larger than the backgrounds. So as soon as we move above, say, 200-300 GeV, we get into a region where signal to background is larger than 1. So a 500 GeV diphoton pair with a mass equal to, in the range 121 to 129 is more likely to come from the Higgs than to come from the background, which again means, all your life gets much, much easier from the experimental perspective. If we look at, in fact, signal to square root of background, which is the significance of the observation and the precision, the inverse of signal over square root of background is the precision with which you can measure a process, you see that 1% corresponds to 600 GeV. So by just looking at Higgs's diphoton pairs with more than 600 GeV in a region where signal to background is a factor of 2, we get a 1% precision on the rate of Higgses. And it will stay below, say, the 10% level all the way up to about 2000 GeV. Again, a regime in which the experimental analysis is simplified. In this context, and Werner, in the next lecture, we will discuss this, we are talking about pile up at the level of 500 or 1,000 events. So the ability to go to very, very, very high PT, of course, takes away a lot of the problems that are met when we try to deal with such high backgrounds. So studies have been performed, of course, not with a full detector simulation in the same way that we can do them at the LHC, but with toy detector simulations at 100 TeV using Delphes. Michele will give you a tutorial on, in fact, tomorrow morning on the use of Delphes. Here is a list of the assumptions that were used in generating signals, backgrounds, and the sources of systematics that are accounted for. The leading systematics in these studies comes from the well, not the leading systematics absolutely, but the leading one in the studies that were done is simply the object reconstruction efficiency. If you see an electron, how precisely do you know that it is an electron? What's the fraction of electron that you identify as such, and with what precision? Okay? The assumptions here are based on the experience from the LHC and the extrapolation to very high energy. So if anything, they should be taken as being conservative, because typically, as for many of the experimental systematics, with high statistics, one can go and pin down the systematics using the data. So the systematics that you will see are mostly related to the ID efficiency for muons, electrons, or photons. Typical systematics that we have in, say, at the LHC include, for example, luminosity. But 4 years from now, when we'll be operating this machine, we will know how to calculate a process like Drell-Yan, the Z boson cross-section, with a theoretical precision which will be much better than 1%. And we will know the PDFs to much better than 1% because there is a parallel electron-proton program. So we will be using the Z counting as a luminometer, certainly with a precision below 1%, not at the per mil level, certainly not at the 10 to the minus 5 level that E plus E minus hopes to achieve, but certainly well below 1%. So to first approximation, we can neglect luminosity as being part of the systematics. And this is a summary for 4 of the most interesting, say, rarest processes, which are complementary to what the LHC can do. This is Higgs goes to 4 leptons. This is the statistical uncertainty as a function of a PT of a Higgs. Starts from per mil. It goes to 1% at the level of 4 or 500 GeV and continues. This is the inclusion of the systematics. The orange line is this ID systematics for electrons or muons. But you see we are at the level of a percent. Now the process H24L is a probe of a coupling of a Higgs to a Z pair. That is measured very, very well in E plus E minus, because in E plus E minus we have a Z boson that goes to Z Higgs. So E plus E minus will measure this thing to the per mil level, 2.5 per mil. So we don't have to measure it better than them, but we have to measure it well enough that we can then make use of their absolute determination of a Higgs to Z coupling and transport it to our determination of other couplings by looking, for example, at ratios of branching ratios. So Higgs to gamma gamma is something that E plus E minus has little statistics and cannot measure very precisely. The branching ratio is 10 to the minus 3 with 1 million event. You mean you have 1,000 events, so clearly at best you get few percent uncertainty. And as you see, this can be measured, again, including systematics, with a 1% precision. So that means that if we take the ratio of Higgs to gamma gamma over Higgs to 4 leptons, by looking at the ratio of these two processes, we don't have to worry about the production mechanism or whatever. We just apply fiducial cuts, a given PT, a given rapidity range for these two final states. We take a ratio and we have a completely free of any uncertainty ratio of Higgs to gamma gamma over Z to ZZ, which we know precisely from E plus E minus, and therefore we can promote this knowledge of the Higgs to gamma gamma coupling to an absolute knowledge of the Higgs to gamma gamma branching ratio. And the same we can do for Higgs to mu mu at the level of better than 1%, and Higgs to Z gamma. So Higgs goes to Z gamma with Z goes to L plus L minus. This process has a branching ratio 10 to the minus 4, so it's very, very rare, and E plus E minus cannot say much about it. These are plots for the ratios now, where the proper account is taken of the correlated or uncorrelated systematics. To detect a muon or an electron are different things, so the two systematics are not correlated. For the coupling to the top, we cannot use a branching ratio because the Higgs doesn't decay to TT bar. So the only way to measure the coupling to the top is to look at the associated production of a Higgs and a top. So it's a new ball game, but here we take advantage of the fact that there is a very, very similar process, which is the associated production of TTZ and TTH. The Higgs and the Z, they have very similar masses. The process is dominated by glue goes to TTH, TTZ. It's very similar processes from the point of view of QCD. So all of the QCD systematics cancel in the ratio, the PDF systematics, the top mass systematics cancel in the ratio, and we just have the ratio of the coupling of the Higgs to the top and the coupling of the Z to the top. The coupling of the Z to the top, of course we know it very precisely from the standard model, but we can measure it without any bias from E plus E minus when we go at E plus E minus goes to TT bar via the Z. Studies have been made of how much, in fact, the theory systematics enters, and the bottom line is that, again, a precision, I will not go through the details of these slides, a measurement at the level of a percent can be performed. Another interesting measurement is the one of Higgs goes to invisible. The Higgs decays to invisible particles when it decays to Z, Z star, and both Z and Z star decay to neutrinos. But the Higgs goes to invisible is very interesting because the Higgs could actually couple, you remember we discussed yesterday this idea of portals, the connection between possible connection of the Higgs with dark matter. So we are very interested in knowing whether the Higgs decays to invisible objects in addition to its own canonical standard decays. And here, by using standard techniques of missing ET plus jet at 100 TeV, the rates are so large that we gain a sensitivity at the level of 10 to the minus 4 in the branching ratio. So here, this plot shows as a function of the integrated luminosity, and the target, as I said, is 30 inverse autobahn, so we are down here. This is the precision or the sensitivity to the branching ratio for Higgs goes to invisible. The different lines correspond to different assumptions about the systematics, so you can even decide to take the most conservative one up here. The yellow line is what E plus E minus can do, and it's limited by the statistics. This purple line is the standard model Higgs goes to neutrinos. And as you see, we get well below, so we'll be able to measure Higgs goes to neutrinos, but then there is also enough sensitivity to measure any branching ratio in the range of 10 to the minus 4 or above, certainly below 10 to the minus 3. If one uses the most aggressive and optimistic projections of the systematics, we go down to the level of a couple, 2 or 3, 10 to the minus 4. Now, this is important because with this measurement of the branching ratio of Higgs goes to invisible, if we turn that into constraints on dark matter coupling to the Higgs, we get this area covered, and this area covers all the way down to the famous neutrino floor for masses which are compatible with a Higgs decay, so masses up to about 60 GeV. So this coverage is absolutely complete, and it's much stronger than that of dedicated direct dark matter experiments. So this is a collection, a table that collects the various precision for different parameters or ratios of Higgs observables and summarize. And as you see, with the exception of the Higgs self-coupling, which is at the level of 7%, that's the most difficult one, everything else is at the level, is below 2%, which means, because these are branching ratios or rates, which means quadratic in the couplings, so the sensitivity to the coupling, the accuracy, is half of the numbers you see here. So we will bring everything in this table down to below the percent, and the branching ratio to invisible to few in 10 to the minus 4. For this, of course, it's important to have the results of the FCCEE. Now, of course, it's important to have absolute measurements of the branching ratios. But I want to stress that even ratios of branching ratios are very important, because the different decay modes of the Higgs really probe completely different dynamics. And with the exception of new physics that would rescale the total width of the Higgs, and therefore that would alter the denominator of every single branching ratio. So if the total width changes, every branching ratio will change, but ratios of branching ratios will not show any deviation. But with the exception of that, any other physics that gets into the game would only affect part of the branching ratios. For instance, if we look at the ratio of the Higgs to gamma gamma and Higgs to ZZ star, the first one is a loop level process, so it's sensitive to possible new particles circulating in the loop. The other one is tree level, so if there are new particles, it's absolutely not affected by it. And if we see a deviation in this ratio, that clearly points to the existence of some charged particle different than those we know. Likewise, if we look at the ratio of Higgs to mu mu over Higgs to ZZ star, again, this is a gauge coupling, it's tree level. This is tree level, but it's related to the second generation Yukawa. So it's got absolutely nothing to do with the gauge structure of the theory. And if something changes this, there is no reason why you should change that, and vice versa. And likewise, gamma gamma and Z gamma, they are both loop processes. However, the charges, the particles that run in the loop, they don't necessarily have the same charge and the same weak couplings. The ratio of invisible to X to gamma gamma, this is a loop level charged, so it's sensitive only to charged particles. This is sensitive to neutral particles at tree level. Any deviation in this ratio would be a clear indication of new physics. There is no question about that. Okay, so even these standalone measurements of ratio branching ratios are very, very important. Here is a slide. I don't have a set of slides on the different, on the analysis that leads to the extraction of Higgs self-coupling, because it's very complicated, but the bottom line is a number in the range of 5 to 7 TeV, and Michele Selvaggi is one of the world experts on this, so you can ask him about it during his lectures. But I want to show you the result of that. We discussed yesterday the issue of first-order phase transition. This is a collection of models in which the Higgs sector is altered and leading to a first-order electroweak phase transition, all of these points. All of these points, in addition to creating a first-order phase transition, they would also alter the coupling of the Higgs to itself, the Higgs coupling, which is 1 in units of a standard model. So you see they would tend to give a higher coupling, and they would also alter the coupling of the Higgs to the Z. If we have a plus or minus, this was done for plus or minus 10% determination of a Higgs self-coupling, I remind you that we expect to get something in the range of 5 to 7%, we would be forced to live in this band. And as you see, we would be ruling out most of these models that give rise to a strong first-order phase transition. FCCEE would bound this from below, so everything that's above this would also be left, would be killed, and therefore we would only be left with a very tiny subset of models in which indeed there is a first-order phase transition, but the effects are too small to be detected either in the Higgs self-coupling or in the coupling to the Z. Needless to say, we're not necessarily after killing models, right? The message here is that while the high luminosity LHeC can only eliminate a small fraction of this model, there remains a large set of possible models in which a first-order phase transition is possible, and that the FCC, EE, and HH would be sensitive to. So that is, properties of a Higgs based on measuring Higgs couplings or Higgs production, say, with the top. There is, and of course I made use in some of those measurements of Higgs is being produced with some PT, 100, 200, 300 GeV as a way of improving signal to background, improving the experimental systematics. But in the first slide I showed you that we can produce Higgses all the way out to several TeVs. And if we do that, all of a sudden we become sensitive to potentially strong deviation in the underlying structure of the electroweak interactions. And one of the reasons why we are interested in having precise Higgs measurements is not because we want to know very precisely the coupling of a Higgs to the top, but it's because we know in the standard model what the coupling is supposed to be, but it's because we're looking for deviations. So it's the sensitivity to deviations from the standard model that we really care about. And one way to achieve sensitivity is through precision. But there are other ways in which we can achieve sensitivity. In particular, we can achieve sensitivity even with moderate precision by just going in regions where that sensitivity is enhanced, for example, by the high energy. And in this slide summarizes the concept I just expressed in words. Let's look at the approach based on an effective field theory to deviations from the standard models. This also Fulvio discussed this morning. We start from our standard model Lagrangian. We add higher order operators suppressed by 1 over lambda square, some scale. We calculate some observable, which is the transition between an initial and a final state, in presence of these corrections, and we get the standard model result plus corrections of order 1 over lambda square. Well, 1 over lambda square is not a number, and we want to have a number. We want a deviation by 1%, 5%, 10%. So we need to introduce a scale. There will be a scale up here. And what is that scale? Well, if we're looking at something like Higgs decays or inclusive production of a Higgs, there is only one scale in the game, which is the Higgs mass or maybe the Higgs expectation value. So these corrections are of order V over lambda, or Higgs mass divided by lambda squared. If we put in the value of V, 246 GeV, that means that if we have, for instance, a 1% precision on a given operator, and if we have a scale lambda of the order of TeV, we have an effect of the order of 6%. Sorry, we have an effect of the order of 6% if lambda is of the order of TeV. So if we have a precision of the order 1%, we are sensitive to lambda of the order of 2.5 TeV. But now let's look at a process where there is another very big scale, maybe a Higgs being produced at very, very large PT, or a Higgs being produced in association with a W with a very, very large invariant mass. So there is another scale in the game, and it is that scale that enters in the value, in the correction due to this operator. So now the correction to the observable is Q divided by lambda. And if Q becomes large, the effect is very large. For example, if we look at an observable where we can claim a precision of 10%, which is not a level of precision of E plus E minus, but it's a very reasonable level of precision for a Hadron collider, if we have a 10%, at a scale of order of 1.5 TeV, for example, if we can measure with a 10% precision the production of a Higgs at 1.5 TeV transverse momentum, that leads to a sensitivity lambda of the order of 5 TeV. In other words, there is an extremely powerful complementarity between super precise measurements of branching ratios, for example, at any plus collider, and what can be obtained by measuring with, good, decent precision, few percent, but at very high Q square in the Hadron collider. And this is a research program that has started only relatively recently, namely the exploration of the consequences of this and direct connection with the impact of the precision measurements, but there are already some results and there are some indications. This is, for example, a study in which one considers deviation of a Higgs PT spectrum from the glue goes to Higgs glue process if there are additional particles in the loop, in particular if there are stops. And one observes deviations at the level of several percents. Here, in this case, it's top partners in the loop, and we're talking about 100% corrections, well, for these models, which are probably already ruled out, but even at the level of 20%, 30% correction at PT in the range of 1 TeV. This is something that the LHeC cannot really see very well, but here we have plenty of statistics to do that. Another example here is deviation induced on the process of associated production of a W with a Higgs. The cross-section is corrected by terms that go like this affect the coefficient of these dimension 6 operators divided by lambda square, and deviations can be particularly large already at relatively small PT. Now, this is true of Higgs processes. This idea of going to very high Q square is also true for Electroweak processes. If one looks at the SU2 invariant expansion of higher dimension operators, one is mixing the W's with the Higgses, so that there is a big interplay between the two, and this has been studied at 100 TeV. I will not go through the detail of this study by, among others, Andrea Wulzer, who will be here in a couple of days to discuss the Muon collider. I will just jump to the results to show you the sensitivity obtained by looking at very high mass Drellian lepton pairs. The sensitivity obtained at FCC at 100 TeV for these two operators, never mind what they are. So we're talking about 2%, 6%. If we compare it against, say, TLEP, which is FCC-EE, you see we have more than one order of magnitude improvement. And it's even an order of magnitude improvement with respect to ILC and to the high energy versions of CLIC at 1 and 3 TeV. So the exploration of Drell-Yan pairs at masses in the range of 3, 4, 5 TeV is extremely powerful and gives us an access to new physics, but this is as a function of a mass of, say, the mass scale at which new physics enters. Direct resonance searches go up to about 40, 50 TeV if we are at 100 TeV, but with this indirect search using Drell-Yan, one can go all the way up to 100 and 200 TeV for couplings which are in the range of Electroweak couplings. This is another slide in which one analyzes the possibility of using the evolution again of a Drell-Yan spectrum as a way of not only measuring the running of a weak coupling, but also being sensitive to possible deviations in the beta function induced by the presence of new electroweak particles. Electroweak particles that maybe are elusive, that maybe cannot be seen from direct searches because they decay in non-visible ways, but if they're present, they will affect the running of the electroweak coupling, and one could be sensitive, for example, to a Wino triplet with mass up to 1 TeV by comparing the Drell-Yan cross-section with the expectations. So these are all things that can be done, just, no matter what. All of these are solid measurements that can be performed, and that can tell us a lot about physics beyond the standard model. There is then the direct discovery reach. That is very simple in a sense, because we have 7 times the energy, so you take any search at LHeC, you multiply by a factor of 5 or 7, and you get the reach. So one can go and do explicitly some of these studies for Z primes, for supersymmetry, etc., etc. They are all listed here. You can look at them in detail, but the bottom line is that you take a limit on the Z prime from the LHeC, you multiply by 5 or 6 or 7, and you get the limit on the Z prime from 100 TeV. And we have examples here for Z primes going to leptons, for new objects, say Kaluza-Klein gravitons decaying to jets, for Randall-Sundrum resonances decaying to Ws, etc., etc. These are gluinos, stops. The bottom line is always the same. This is a table of supersymmetric particles with the reach at 14 TeV. You multiply by 7 and you get the reach at 100 TeV. Dark matter is interesting because this, while for a gluino going up by a factor of 5 just shifts the gluino limit, with dark matter, if we get up to about 1 to 3 TeV, depending on whether it's a Higgsino or a Wino, means saturating the range within which we expect a WIMP. So this factor of 5 or 7 is precisely what we need in order to finally detect or finally exclude the possibility that dark matter is a WIMP. So this is the nature of the studies and of the results that are emerging. Additional Higgses, for example, in supersymmetry, can be probed up to masses in the range of 10 to 20 TeV, and that, of course, has implications on our ability to explore, again, extensions of the Higgs sector that could give rise to a strong first-order phase transition. So the machine is designed for being 100 TeV, but maybe, we may need 200 TeV. Well, answer to this is that we don't know how to build a 200 TeV machine, certainly not in Europe, so there is no point in discussing it, and I believe that 100 has shown that there are several thresholds for which 100 is indeed the minimum that we would want. To have more, of course, would be better, but 100 already could provide definitive yes or no answers to some interesting questions, as we discussed yesterday. The other alternative is that, one could be a bit less ambitious and be enough with 27, which is this famous high-energy LHeC. That would become interesting in several scenarios. One is that the LHeC discovers something, and then if we double the energy, of course, we would be producing much more of it. and therefore we can start studying this new physics effectively without having to wait for a 100 TeV machine. Otherwise, we would just be doubling the mass reach of the LHeC because we have twice the energy. We would improve on the Higgs coupling measurements. We would improve on the Higgs self-coupling measurements. So we would be doing marginal improvements to what the LHeC is telling us, and whether it's worth the effort of doubling the energy, we will have to judge once we know more from the LHeC. Here I have some slides. For example, this one confirms that indeed, as a function of a mass that you could discover at the LHeC, this tells us what is the mass that we can discover at high energy LHeC, depending on whether it's quark-quark, glue-glue, or quark-glue on initial state. And for all of them, you see that pretty much you always double the reach. So it's a trivial, you don't have to be to have a PhD to make that conclusion. In some cases, doubling this energy could be interesting. There are classes of this so-called natural supersymmetry, where one sets some constraints on what natural really means, and then this is the scatter plot is a set of models. The LHeC can reach up to here, high energy reaches up to here, and as you see, rules out pretty much all of these class of models. So one can pretty much cook out cases in which that factor of 2 energy is relevant. The Higgs, this is the ratio of the statistics at 27 over 14 TeV. At 27 TeV, we expect 5 times the luminosity, but you see the gain in statistics is only like a factor of 10. So the actual cross-sections only go up by a factor of 2, and then we gain a bit because of the luminosity. So we are not really improving on the Higgs program of the LHeC dramatically by going to 27. We do measure, however, the Higgs self-coupling with a precision of about 30%, which is interesting, at 95 or 15% at 68% confidence level. Let me just come to the conclusions. So I think that the future high-energy PP collider is necessary to extend and complete the exploration of the TeV scale. In the case of Higgs and Electroweak symmetry breaking, it complements E plus E minus in bringing below the percent level the measurement of Higgs couplings. Everything that the things that E plus E minus cannot do, at least related to second and third generation PP can do at the percent level. It pushes below 10% the Higgs self-coupling, extends to the multi-TeV region the search for additional Higgs bosons, and therefore extensively covers possible models with first-order phase transition. It provides an alternative high-energy probes of higher dimension EFT operators, again, therefore complementing the precision with the reach in energy. For dark matter, it extends to the few TeV region the sensitivity to WIMPs, in most cases closing the WIMP window. Via Higgs to invisible, it probes a huge range of Higgs portal models. For what concerns naturalness and all of the particles that may come to explain it, and in general BSM, say new gauge interactions, compositeness, etc. It extends by a factor of 5, 7, occasionally 10, the direct mass reach. With better detectors and higher precision, will also improve the indirect reach. And finally, I haven't discussed this, but there is the EPIC program that carries its own benefits, and there is also the possibility of having heavy ion collisions, which again, I didn't discuss. Thank you.
Questions?
Hi. I did not fully understand how you can exclude the WIMP hypothesis from this heavy, for this high energy hadron collision, because in principle all the searches for WIMPs are made using low background experiments like xenon or argon with noble gases. So I would like you to comment more on this.
Well, the underlying physics is what I mentioned yesterday. Namely, there is an upper bound to the mass that a WIMP, what is defined as a WIMP, can have. Because when it's heavy, it's produced abundantly in the early universe. And then when the universe freezes out, all of those WIMPs, I mean, if they are stable, they have to decay, because otherwise we would be over-saturated by dark matter. And by imposing how strong a cross-section can be for their own annihilation so that they disappear, and introducing constraints that come from, say, unitarity, but even just out-of-model building, you get an upper limit. So for weakly interacting, WIMP literally means weakly interacting, so it means that they have to decay via weak interactions. And therefore, in that case, the mass limits are in the range of 1 to 3 TeV, depending on whether it's a SU2 doublet or a triplet. And the ability of, and the reason why the 100 TeV machine can close this window is because it has access to the 1 TeV or up to the 3 TeV mass region. So this is the way you can conclusively rule it out.
But does this mean that we will be able to see some signal coming from the decay of these WIMPs?
No, you don't see the signal from the decay. You see the production. You see the missing energy signature or other equivalent signatures.
Okay, thanks. Yeah.
Other questions? Comments? Okay, thank you again. Michelangelo. So next lecture by Frank Zimmermann. We are downloading the last version of the.
Okay, good afternoon. So this afternoon we look at the machine aspects for the Hadron colliders. Can I go here? No. Very strange. No. Something's wrong. How do I go forward? Good. Machine aspects for future PP colliders. We have only 2 sites. At the moment we have the LHeC, as you may know. And it defines the present frontier collider. And the performance is excellent. We are already very close to completing 60 inverse femtobarn this year, which was the target for 2018. And we are well on track to go to 300 inverse femtobarn before the LHeC high luminosity upgrade. So at 13 TeV we have an excellent machine, and we know how to operate and build such a machine. So how will it look in 25 years from now? We think that the Very Large Circular Hadron Collider is the only feasible approach to reach 100 TeV center of mass collision energy in the coming decades. And as Michelangelo showed, this gives access to new particles via direct production in few TeV to 20 or 30 TeV mass range, far beyond the reach of the LHeC, and much increased rates for phenomena in the sub-TeV mass range, much increased precision with respect to the LHeC. And as a very simple formula, for the energy reach of a Hadron Collider, there are only 2 parameters which matter, which is the magnetic field of the dipole magnets and the bending radius. So because energy or momentum is directly proportionate to the product of magnetic field and bending radius. So compared to the LHeC, for the future collider, we want to build a 4 times bigger machine, which gives us a factor 4 in the bending radius. And we want a 2 times higher field, which gives another factor of 2. So together we get factor 7 or 8 an order of magnitude in the center of mass energy. Actually not easy. It's not easy to increase the field, and it's not easy to build a bigger machine. So we push both these parameters as much as reasonable for the coming decades. Why do we not build a linear Hadron Collider? This morning we were told that linear machines go to much higher energy. So why does nobody want to build a linear Hadron Collider? Any idea? Anyway, suppose we use ILC technology, then we have a gradient 250 dB over 11 kilometer. Real estate gradient is about 23 mega electron volt per meter. If you want to go to 100 TeV, we need a 4,000 kilometer linear collider to go to the same energy as a 100 kilometer circular machine. So So I think it's clear for me that we need a circular tunnel. And whoever builds a circular tunnel will probably build also the next 100 TeV Hadron Collider. So we have this FCC study, which was initiated in 2014, following the previous update of the European Strategy for Particle Physics, which is an international collaboration with CERN as a host laboratory. And the main focus of this FCC study is to design a Hadron Collider with 100 TeV center of mass and 100 kilometer tunnel, as shown this morning, roughly this magnitude here, limited by the Jura on one side and by the Alps on the other side, and also crossing the Lake of Geneva, but at a location where the lake, where's this thing? At a location where the lake is relatively shallow, maybe 20 or 30 meter in depth. So then the E plus E minus collider FCCE could be installed as a possible first step. In addition, the study includes also electron hadron collider option. Electron beam would come from a different machine, from an energy recovery linac, and collide at one point with the hadron beams circulating in this FCCHH. And we are studying also high energy LHeC upgrade mentioned by Michelangelo, which is an upgrade of the existing LHeC using the magnets developed for FCCHH, so replacing 8.3 Tesla magnets with 16 Tesla magnets to double the energy of the LHeC. On the timeline, this shows you the history and the present plan for circular colliders at CERN. There was lab design started, as you also saw this morning, in the second half of the 1970s. It was constructed in the middle of the 80s, and it operated until 2000. LHeC had a much longer life. Design started in 1983. Sorry, I don't know. It doesn't go exactly where I think it should go, but okay, never mind. Then construction of the LHeC started around 2000 when lab was completed, and the physics started in 2010 and still operating. And around 25 we will have the high luminosity LHeC upgrade, and the high luminosity LHeC will operate until around 2037. So all these projects take a long time. So if you want a machine after the high luminosity LHeC, we have not so much time left. So we have actually less time left than was available to design and build the LHeC. And the FCC is perhaps a more complicated machine. So the FCC study, we try to advance fast to be ready for the period 35-40. And our actual milestone is to deliver the input for the upcoming update of the European strategy. So we should deliver a conceptual design report for all these machines by the end of this year. But this shows you, there were not so many hadron colliders in history. This shows you all of them, the past and the proposed future colliders on a double logarithmic scale. Vertical axis is the peak luminosity, horizontal axis is the center of mass energy in TeV. The first machine was the intersecting storage rings at CERN. It had, for that time, incredibly high luminosity, more than 10 to the 32 in the 70s, and that actually was a world record for all colliders for 20 years, and for hadron colliders, I think it was a world record for about 30 years. Then there was the SPP by S, ISR was a proton-proton collider. Then there was SPP by S, and Tevatron was proton-antiproton colliders, and now we have the LHeC. And the LHeC also includes the high luminosity LHeC, which is expensive, but it's still an upgrade of the existing machine, so it's more or less, it has the same arcs as the present collider. And then we have the future machines shown on the right upper side. High energy LHeC, FCCHH, and the SPPC in China. So there was actually something like an order of magnitude jump from the SPP by S to the Tevatron in luminosity and energy. There was a jump like this from the Tevatron to the LHeC, and it seems reasonable that we should have another jump of that same order of magnitude going from high luminosity LHeC to FCCHH. If you only go to high energy LHeC, the jump is much less impressive. But if there's some sign of new physics, of course, it could be worse to make a smaller jump to make a definite discovery. I have again some formulas. Actually, you know already this formula because we had it this morning. If the peak luminosity is limited by synchronization power and by the beam effect, we can again combine the formulas. Actually, constant is only different now because now I replaced electron mass everywhere by the proton mass. At 100 TeV, also the synchronization of the protons becomes quite important and becomes a limitation. So we have actually a few megawatt synchronization power in the proton beam at this energy. So we cannot accept, it's very difficult to cool away this synchronization from inside the cold magnets. So that's also a limitation. And the beam effect is a limitation as it is for the lepton colliders. So we can combine these two expressions and replace some, this general luminosity formula. We can replace some of these variables using the constant maximum beam tune shift and the constant value for the synchronization power. And we get this formula, which is very similar to what we saw this morning. Luminosity goes linearly with the size of the machine, linearly with the synchronization power, and 1 over beta star. As another possible limit, if the detector cannot handle the high luminosity, we could be limited by the maximum event pileup in the experiments. And then we can introduce another constant, which is this one. Goes with the inelastic cross-section and the bunch population square. For example, there are some values, I don't know, maybe these might be outdated. Werner, Riegler has the latest values, but roughly these are all of the order of 100 millibarn. We can use this also to modify the luminosity formula, and we arrive at a very simple expression. If we are limited by the pileup, the maximum luminosity is actually given by this. We have only one free parameter, which is the number of bunches. So if you want more luminosity, we need to increase the number of bunches with less charge per bunch, for example. So in that case, going from 25 nanosecond LHeC spacing to 5 nanosecond spacing would help. These are the parameters. On the right, you have the LHeC design. Then next to it, we have the high luminosity parameters. And then there's FCCHH with an initial configuration and the nominal configuration, also called phase 1 and phase 2. And then there is a high energy LHC. So you see the dipole field is 16 Tesla for both FCCHH and HE LHC. The collision energy is of almost factor 4 different. Circumference is of course different. And the beam current, in the case of FCCHH, the beam current is very similar to the present LHC. For the high energy LHC, beam current is higher. It's the same as for the high luminosity LHC. So we have these beams available at CERN, and we can directly inject this type of beam from the existing injector complex or from the existing LHC into the FCC or HE LHC. Bunch intensity also is the same beam. For the FCCHH, we have 10 to 11 protons per bunch, the same, slightly less even than in the LHC design. And for the high energy LHC, we have the same number as for the high luminosity LHC. At the moment, bunch spacing everywhere 25 nanoseconds. Synchronization per beam, per ring, is much higher than for the LHC. LHC has about 3.6 kilowatt per beam. For the FCCHH, we have 2.5 megawatt per beam, so 5 megawatt in total, which is a challenge. And for the HE LHC is not quite so as bad. We have 2 times 100 kilowatt. So in terms of synchronization power per length, we have these values around 28 watt per meter per aperture or 5 watt per meter per aperture, which has to be compared with 0.2 watt per meter per aperture in the present LHC. So we have a lot more power, factor 20 or 150 times more power per unit length that we have to extract from inside the cold cryostats of the magnets. What's interesting is that this is a nuisance, and it's actually electrically, we need a lot of electrical power to remove this heat at very low temperature. On the other hand, we also have some benefit. We get a nice damping. A damping time, longitudinal damping time in the LHC is about half a day. And in the FCC, it's half an hour. And for HELC, it's 2 hours, and transverse damping time is 2 times longer. So for these machines, we have significant damping thanks to the synchronization. So we don't need to worry less about beam quality, and actually sometimes the beam damps too quickly, and it actually becomes too dense, and we get into trouble with the beam effect. So it's a nice feature, but it's needs to be the shrinkage due to this radiation needs to be controlled carefully. The beta star, this beta at the collision point, is very similar, actually somewhat relaxed with respect to the high luminosity LHC. Emittances are more or less the same. This emittance for high energy is the same. Here it's slightly smaller, but the intensity is also less. Peak luminosity is shown here. High luminosity LHC could reach probably 2 × 10⁻³ or so, but it is leveled at 5 × 10⁻34. FCCHH starts at the same value, 5 × 10⁻34, and in the nominal phase it goes to 3 × 10⁻35. High energy LHC has about half the luminosity. And in terms of pileup, it means that the FCCHH at 25 nanosecond spacing has 1,000 events per crossing, and high energy LHC 460, while the target for high lumi is 130. So we need to go something like factor 3 or 6 beyond high lumi in order to have the detectors ready for the 100 TeV or 27 TeV collider. Also, the energy stored in the beam is enormous already. The LHC has half a gigajoule stored in each beam. For the FCCHH, we have 10 gigajoule. That's an enormous amount of energy, so we need to carefully control the beam and have a very safe machine protection system in order to prevent the machine from self-destruction, because this beam can destroy many magnets if it is lost in an uncontrolled way. This is the layout. Layout is very similar to the LHC. It's just somehow inverted. We have the two main experiments in points A and B, similar to LHC and Atlas, and then we have secondary experiments and injection here on the two sides of point A. This is like LHCb and Alice. We have these L and B where we have injection and a secondary experiment. Then we have RF section here and the momentum collimation, and then the two longest sections, which are 2 times longer at the moment than the other experiment, the other straight sections, are these sections for transverse betatron collimation, which is also related to the machine protection issue. We need very large beta functions to have reasonable size gaps and to ensure the survival of the collimators in case of a machine failure. And we have also need a lot of space, and we need long kicker sections and scepter magnets to extract a 50 TeV beam from the machine in case of a failure. I think I said most of this. The present layout and the location is compatible with using either the LHC at the low, not at the 7 TeV, but at 3.3 TeV, or the SPS as an injector, the SPS tunnel, that is. Circumference has been optimized and is at the moment 97.75 kilometers. This is a day at the high luminosity, at the FCCHH, over 24 hours. In the first initial phase, we have something like almost 2 fills per day. We start at 5 × 10⁻34. If we don't do anything, the luminosity decays like this. Actually, we need to do a little bit. We need to keep the beam limit at a certain value, and then we get this type of behavior. We have 11, 12 hours long fills, and then after a few hours turnaround, we get a second fill. In the phase 2, phase 2 is at the same beam current, but with a smaller beta star, and we accept a higher beam tune shift. This type of beam tune shift of 0.01 is the LHC design for the maximum beam tune shift, total tune shift over 2 or 3 IPs. And if LHC already showed that it can operate with 3 times this nominal tune shift, if we assume that FCCHH can do so as well, we can get the nominal performance where we burn off almost all the protons, and we fully exploit the shrinkage due to the radiation damping. We get very high luminosities with a peak close to 3 × 10⁻35. The beam current is the same, 0.5 ampere unchanged, and the synchronization power is also the same for the initial phase and for the nominal phase. Here's some details. The luminosity plot you have just seen. You can see the corresponding integrated luminosity. Of course, this is for the ideal machine without any failure. You can see that in phase 1, we could accumulate about 3 inverse femtobarn per day, and in the nominal phase, maybe 9 inverse femtobarn or something like this. In phase 1, we burn off about half the protons at the end of a fill. In phase 2, we burn off more than 80% of the protons. So the phase 2, the normal operation is extremely efficient. We really burn away the protons, and when the beam is dumped, less than 20% of the protons are left over. As I said, in the initial phase, we need to inject transverse noise to keep the beam tune shift constant, and that means we slow down. Normally, the emittance decreases like this, very fast damping due to the synchrotron radiation. In the initial phase, we don't want to accept such a high beam tune shift, so we inject noise to slow down this decrease, and we follow this path. In phase 2, we have this fast damping, and the beam tune shift increases during the fill, as you can see here. In phase 1, we limit the tune shift to the LHeC design value. In phase 2, we go to a value that the LHeC has already demonstrated. And all of this is then reflected in the event pile-up per bunch crossing like this. In phase 1, in the initial phase, actually event pile-up stays below 200, and in the nominal phase, we reach this value close to 1,000. Okay, if this pile-up is too high, we can also do leveling. As we do leveling in high luminosity LHC, we can also do leveling in FCCHH. And it's actually quite attractive. This is example of leveling with 25 nanoseconds. This is the green curve, average luminosity inverse femto per day as a function of the target luminosity. So if we don't go to 3 10 to the 35, but if we go, for example, to 1.5 10 to the 35, where we have half the pile-up, 500 events per crossing instead of 1,000, then in the average luminosity, we lose this difference, which is maybe something like 20% loss. Reducing the pile-up by factor 2 by leveling loses 20% in average luminosity. That might be acceptable, and we could go down further, but then the loss becomes more prominent. Okay, we have 2 injector options. We are very fortunate that we have already the LHeC, so we can use the LHeC at a reduced energy as a beautiful injector. And the layout is shown here on the left. We have new transfer lines which connect the LHeC and the FCC. So we can inject either in this direction, and we can inject on the other side into the FCC like this. So we need about 5.5 kilometer new transfer lines with 7.2 Tesla magnetic fields. The other option is to build a superconducting SPS at a low energy. We can go to 1.3 TeV in the SPS tunnel and inject from the SPS tunnel. The location of the present design is chosen that we can use either option. Here we would need 6.5 normal conducting bands at 1.8 Tesla for the new transfer lines. So the baseline is to use the LHC. And then in that case, the fields that makes the FCCHH easier. The field swing of the FCCHH is then a similar factor between injection energy and top energy as for the LHC. On the other hand, it would be cheaper and would have some other advantages to inject from the SPS tunnel. We could inject more bunches at the same time because the machine, sorry, I need to go one more back. Because the injection protection is easier at the lower energy. And also, LHeC needs a lot of energy to operate. We would save a lot of power if we could eliminate the LHeC and inject from a new fast cycling machine in the SPS. Also, we could inject perhaps a little bit quicker. The magnets that we need in the Super SPS are similar to the CIS 300 magnets developed for the FAIR project in Germany. And by the way, the Super SPS would be the ideal injector for the high energy LHC as an alternative to the 450 GeV present SPS, which looks very difficult as an injector for the high energy LHC. By the way, concerning cost of future accelerators, we have this nice graph from Philippe Lebrun. You can see the specific cost in 2008, mega Swiss franc per GeV center of mass energy for different accelerators at CERN. And you see a trend. The total costs went up with about one-third power of the center of mass energy. So we see, so the specific cost decreased. And if we use this scaling, which maybe is too optimistic, but if we assume we stay on the same scaling, then a 100 TeV collider would cost about 1.8 times the cost of the LHC. In order to do this, we need a new technology. By the way, the reason why the cost increased is, of course, that new technologies were invented, superconducting magnets were introduced, and then we went to the proton-proton collider from the PP bar collider. And also LAB had superconducting RF cavities. Anyway, we need a new technology change in order to stay on the slope. And the present plan for the timeline that we have is to use a new superconductor, niobium-3 tin, instead of niobium titanium. You can here see the critical current at 4.2 Kelvin. Niobium titanium decreases very steeply and goes to zero at around 10 Tesla. So we operate the LHC at 8.3 Tesla, which is somewhere where it tilts over. Niobium-3 tin has about 2 times higher critical field, as you can see. So we want to go from 8 Tesla to 16 Tesla by changing the material. You can also see the high temperature superconductor, which look much better, like bismuth 2212, actually doesn't turn over at all. But this material is even much less advanced and is much more expensive than niobium-3 tin. So if we want a machine in 2040, this is not an option at the moment. This shows you the history of niobium titanium production. The first machine, the first super accelerator with niobium titanium was the Tevatron in Chicago. And sorry, this is the performance. This is a critical current improvement. This is the Tevatron, and then you can see improvement in the critical current thanks to the developments for the superconducting supercollider in the US. SSC has doubled the critical current, and the LHeC has even slightly higher critical current than the SSC. So for the niobium-3 tin, we start on this right scale, and there has been some improvement thanks to US core development program. So there's also a steep increase in the slope of critical current. And this was initially driven by the ITER production for the ITER fusion project, which uses a significant amount of niobium-3 tin. But with a wire quality which is not the same, we need a much better quality for the accelerator magnets. So, and then we have the high luminosity LHeC program, which is developing a few tenths of magnets based on niobium-3 tin with a field of 11 or 12 Tesla, and this is an important technology step, an important milestone to go to the 16 Tesla that we want to have for the FCC. So this is the high luminosity. The blue curve here is the critical current versus field for the high luminosity LHeC. This is the existing wire, and we have some prototype magnets based on this wire. And the target for the FCC wire development is to improve this by 50%, to go from 1,000 at 16 Tesla, to go from 1,000 amp per square millimeter to 1,500 amp per square millimeter. And the consequence of this increase is a significant reduction in the cross-section of the magnet. I think there's a picture, yes. If you use LHeC wire, the magnet cross-section wire of the wire would be like this of the cable. And if we go to the target for the FCC wire, we can reduce the area by almost a factor of 2. This is a significant cost saving on the niobium-3 tin. And also it will make the magnet smaller. As you will see later, we have enormous space limits in the existing tunnel. We need compact magnets, so we have a double benefit. We reduce the cost and we reduce the size by making the wire more performing. So the conductor activity started with several collaborations. Important collaborations are with Russia, with Japan, through KK, and with Korea. There's also Columbus company, Italy, University of Ginevra, Technical University of Vienna, SPIN in Italy, and University of Freiburg in Germany. And some other activities are planned with a big producer, Burka, in Germany, which is producing the wire for high lumi LHeC, and with this company in Finland. Anyway, the Russians, the Japanese, and the Korean effort, they all produced wire for ITER, and they are, I think, happy that they can now work on superconductor for accelerator project following this ITER development. And in the first year, within less than 1 year, these three partners already produced wire of the same quality as the high luminosity LHeC wire, as you can see here. After only 1 year of development, some of these, like Bochwa and Koreans and they have already wire which has a similar performance as the high luminosity LHeC. So this is very encouraging, and we hope that they can now improve the performance and go to the level that we need for FCC. We have different magnet designs, and we are comparing different design options. LHeC and the Tevatron and Hera, all the previous machines had a cosine theta type of magnet, which is shown here on the left, cosine theta coils. There are other designs are possible. There is a block design, there's a common coil design, and there is also a canted cosine theta option. And there is, I think there is one more. Anyway, we have these 4 different designs, and 3 of them are studied within a European framework supported by the EU, so-called Eurocircle collaboration. This cosine theta by INFN, Italy, block designed by CA in France, and the common coil by CMAT in Spain. And we are lucky that we have a special Swiss contribution which gives money to PSI to develop the canted cosine theta design. And this is accompanied in the US by US Magnet Development Program. 2 of these designs are also built. Actually, they maybe were pushed in the US. LBLNL Berkeley is working on the canted cosine theta. They have been working on this for a long time, and Fermilab is working on the US version of the cosine theta magnet. So we hope to have short model magnets built. Actually, they're underway. Some are already being built from now on until 2022. And we're happy that a Russian 16 Tesla magnet program was also launched by Novosibirsk recently. And we hope also to get results from this Russian program. Here's an example from CERN, this is US example. Actually, 15 Tesla dipole demonstrator cosine theta has already been put together at Fermilab. You can see the photographs of the components and of the complete magnet. Actually, first magnet tests are ongoing this month. So September is almost over, so we should hear some results very soon from this first dipole, 15 Tesla dipole demonstrator. That will be quite exciting. At CERN, we are also building 16 Tesla enhanced racetrack magnet coil, and you can also see the components. All the pieces are in place for the first coil. Binding of the first coil has been completed. And I think also this fall, the magnet should be, this demonstrator coil should be assembled, and we can test and see if we can reach 16 Tesla. This is the schedule for the magnet program. It's on a logarithmic scale, and the total duration is 20 years. You can see units is in tons. We are starting at a very low level, at a few tons per year, and this should go up to thousands of tons, 10,000 tons per year. So we are in this phase of short models, and then this should be followed by long models and prototypes in the second half of the 20s, and then pre-series, etc. Total duration 20 years. And it's tailored such that it follows exactly the LHeC Nairobi tin program. So when the LHeC Nairobi tin, when the industry has finished the high-lumi LHeC magnets, they can directly continue with long models for the FCC. So they can directly, after developing 11 and 12 Tesla magnets for high-lumi, they can directly go to the 16 Tesla for the FCC. And they have all the infrastructure available, so there's a very fortunate timing. So now I want to say a few words about the high-energy LHeC. High-energy LHeC is not an easy machine. Actually, in many regards, it's more difficult than the FCC HH. First of all, there is a push to make LHeC as simple as possible. And in particular from the US colleagues, we get a push to inject from the existing SPS. But it's quite difficult because the field quality at this energy is extremely poor. If you have a 2070 V collider, we inject at 450 GeV. We have a huge energy swing, and for niobium tin, the field quality is already much worse than for niobium titanium. And in addition, the beam is much larger than for FCCHH. The conditions are very unfavorable compared to FCCHH and compared with the LHC. In addition, the magnet bore, the cold bore is smaller, and the beam screen inside the magnet is much thicker, so we have much less physical aperture. We have about 60% of the physical aperture available in the LHC. So we have a big beam and we have less physical aperture, so it complicates collimation and protection. Then we have a problem that the tunnel layout is completely frozen and the straight sections have a limited length. So we cannot use, for the FCCHH, we applied some length scaling. That's why these collimation sections became 2.8 kilometer long. In the LHC, everything is fixed in the tunnel, so we have to stay within the existing length. And already the occupancy is quite high, so we need to double this in the collimation insertion. We have warm magnets because of the debris from the collimators. We cannot put superconducting magnets. So it's very difficult to stay within this existing length, doubling the amount of normal conducting magnets. I don't know if I said this very clearly, but it's already very crowded, and it's very difficult to put more magnets in the available space to cope with twice the energy. This complicates collimation at top energy enormously. And next, the magnets must be bent because we have a significant surge jitter in the tunnel, and we would lose too much aperture if the magnets are straight. So the FCCH magnets can be straight with a bending radius of 12 kilometers, but with a bending radius of less than 3 kilometers, the magnets must be bent, as they are for the LHeC. And for the LHeC, the magnets were put in a mechanical press and bent after production. If we do this after the processing of the nucleus becomes very brittle. It has not been demonstrated that these magnets can be put into a press and bent without damage to the superconductor. And this we will only know using some prototypes in a couple of years at the earliest. And we have a limited transverse tunnel cross-section, which restricts the transverse size of the magnet cryostats. So I show you some illustration. First of all, we need a better wire than ITER and high lumi LHeC. We need a wire with a filament size of 20 micron instead of 50 micron. This improves the so-called persistent current effects, and this is needed, of course, for FCCH and for high energy LHeC. But this is not enough. In addition, we must use a new idea, which I think came up in 2017, which is, or maybe 2016, which is to introduce so-called artificial pinning centers inside the superconductor. So we must make two technological steps here: change the filament size and introduce artificial pinning centers. And then there are some questions how efficient this artificial pinning of the fluxes inside the superconductor can be. At the moment, it's believed that 50% pinning efficiency is a reasonable target. And so you have these different hysteresis curves for the sextuple component of the dipoles. The sextuple determines the dynamic aperture, more or less. So you can see these different curves and different target injection energies. Injecting at 1.3 TeV is here. Oops. No. Is here. And we are on the rising edge, on the rising curve, part of the curve for all of these cables. And it looks quite good, actually. Injecting at 900 GeV is another option. And we are okay, except for the case without artificial pinning. And injected at 450, we are actually at this peak, at the extreme point of the B3 curve. It's probably not a good place to be. In some of these cases, we have in simulations 1 sigma dynamic aperture. So we know we are safe at 1.3 TeV, but on the other parts, there are a lot of uncertainty on the real behavior of the cable. So there's a lot more work to be done, and this is ongoing. We are waiting for a new error table by the end of this month right now to make an update on the dynamic aperture for the high energy LHeC. But it's not an easy study. The FCCH can inject at a more favorable position. And this shows you the tunnel. High energy LHeC is in the existing tunnel with a tunnel diameter of 3.8 meters. We assume that we don't want any major civil engineering modifications of the tunnel, and this limits the maximum magnet cryostat diameter to 1.2 meters. The present LHeC magnets have 1.1 meters or so. So we have basically the same magnet size, slightly larger than the present magnet, but we need to provide twice the field. Also, it's quite difficult. And we have a larger QL because we have much more heat to extract from the tunnel. So this cryogenic return line, it's much bigger than in the present LHeC. So the tunnel becomes very crowded. So our design drives us to develop a compact 16 Tesla magnet. Of course, if it can be done, it will also simplify the tunnel for the FCCH. So this is development. Initially, we had a cold bore 800 millimeter. This has been reduced to 600 millimeter in order to comply with the high energy LHeC constraints. In addition, we need additional cooling cryoplants. We need additional underground 1.8 kilo Kelvin refrigeration units because we go from a full sector cooling to half sector cooling. Otherwise, the QL would need to be even larger than it is already. So we cool. Doesn't work. Anyway, we cool only half a sector, and we need these additional red underground cryoplants, and we need also 8 new high-power 4.5 Kelvin cryoplants on the surface. So it's not a minor investment, these changes. Here shows you the IR layout for the experiments. On top is the LHeC. The final focusing is done by a triplet, this quadruple triplet, which starts at 23 meters from the collision point. And then in the LHeC, we have warm bending magnets, first the D1, and then a supermagnet D2. And a quadruple. In the high luminosity LHeC, the triplet becomes longer because we have a smaller beta star and we need to open the magnets and we need longer magnets for the focusing. So we have this configuration and we have a superconducting D1. For high energy LHeC, the triplet becomes longer. It's almost twice the length of the LHeC, and all these magnets are stronger. and we leave space here for so-called Krebs cavities. Both high luminosity LHC and high energy LHC will need to operate with transverse deflecting cavities to restore the overlap of the colliding bunches at the collision point. Okay, concerning radiation of the final triplets, one reason why we need to do the high luminosity LHC is that the triplets will be destroyed after 300 inverse femtobarn. For the high energy LHC, we consider a shield, 2 centimeter inner tungsten shielding in the final triplet, and the simulation suggests that with this shielding, we can survive 10 inverse autobahn integrated luminosity with these final triplet magnets. So it looks quite good. Maybe we don't need to change the triplets during the lifetime of the high energy LHC. We also have an optics with 23 meter L star and with the existing lengths of the straight section. This was thought to be very difficult, but our very young collaborator from Oxford, Leon van Riesenhaupt, he managed to find a solution very efficiently in a rather short time. Then we have the Chinese project. For completeness, I mentioned this. This is the SPPC. And if they build the CEPC, I think there is no reason why they would stop and not also build the SPPC afterwards. They have actually a different design. While the CEPC looks very similar to FCCE, the SPPC looks quite different from FCCHH. So they have an initial phase with 12 Tesla dipole magnets, and then an ultimate phase with 4.2. That means the center of mass energy initially is 75 TeV, and later they might go even to 150 TeV center of mass. This is the layout. They assume a coexistence of the E plus E minus and the proton collider, and also have EP collisions between the two colliders. So there are 4 IPs in the tunnel. So for the Hadron Collider, there are 2 PP collision points, 1 ion-ion collision point, and 1 EP collision point. Then they have 1 collimation insertion, 1 RF insertion, extraction and injection insertion, and they have a green field injector chain. Unlike us, they need to build this entire proton injector chain. This is shown here, consistent proton LHeC, rapid cycling synchrotron, and then 2 synchrotrons. What's interesting, they want to use a different type of superconductor, ion-based high-temperature superconductor, which was discovered in 2008 in Japan. And this is the present performance is somewhere here, indicated by this red line here. This is in 2016. This is here 28 Tesla. 10 Tesla, this is the present performance. They have a 10-year development program to push this performance up by a factor 10 and at the same time reduce the cost by a factor 10. So basically a factor 100 improvement in performance per cost over 10 years. Quite ambitious program. But if they succeed, that could also become interesting for us. If we first build the FCCEE, we have more time also to develop magnets for Hadron Collider. And if they manage to improve their performance and reduce the cost, this could become quite interesting. So they set up a consortium with many different companies and institutes to develop the superconductor, and they produced already 100 meter. Already a time ago, 2 years ago, they produced a 100 meter ion-based HGS wire at this Chinese Academy of Science. But this is only enough to build maybe a centimeter of magnet or so. So they need a lot more, but it's a good beginning. And they have also a different coil layout. As you can see here, they have the 2 beams on top of each other and not side by side. So actually this magnet design is also different. So actually, while in the lepton E plus E minus side, everything looks the same, on the PP side, it looks quite different. The magnets are completely different from our magnets. So this is quite nice, and we might learn something from this Chinese development. One last item I want to mention is the synchrotron radiation for the proton. I said it's very high. We have 30 watt per meter per beam. So we developed a new beam screen, rather complex beam screen. This sits inside the cold bore of the magnets, and it has an outer structure and an inner shell. And it has pumping slots which are here, which are hidden by this inner part of the structure. And it has huge cooling capillaries, much, much bigger than the present cooling capillaries of the LHC. So we can put significant amount of cooling liquids through these cooling capillaries to extract the heat. And then there is some opening where the synchrotron radiation goes through, and there's a rough surface, so-called sawtooth structure here, to keep the photons on this outer side and avoid reflections back into the inner part of the chamber. And then these pumping slots, which are quite large, they don't pose any impedance by the beam because they are shielded by this inner shell. So it's a quite ingenious design, has been improved in several iterations. Here's one picture of one of these designs. And we are testing this design with beam in the synchrotron light source Anker at Karlsruhe in Germany. Actually, the Anker light source has an electron beam with basically the same synchronization power spectrum, both in the photo energy content and in absolute flux, exactly the same as what we will have in the FCCHH. So 3 different prototypes have been tested with the synchrotron light in Anker, and the behavior is as expected, but the design has been optimized as a result of these tests. And the temperature of the beam screen has to be optimal. In the LHeC, the beam screen is between 5 and 20 Kelvin. And in the FCCHH, we need to increase the temperature. It's easier, it's more efficient to extract heat at higher temperature because the Carnot efficiency improves. And this shows you there are 2 effects, actually. It's easier to cool the beam screen, but if the beam screen is hotter, it radiates more to the cold bore, and the cooling of the cold bore becomes more complicated. So there's an optimum depending on the total power that is hitting the beam screen. This you can see in these curves. And for the power of 28 or 29 watt per meter that we are talking at 1.9 Kelvin cold bore, you see we have a rather shallow minimum between 50 and 70 Kelvin. So we need a higher beam screen temperature than in the LHeC. There are some negative consequences. There are other constraints. If the temperature becomes too high, the resistivity of the wall increases too much, and we get problems with beam instabilities. And also there are favored temperature regions favored for the dynamic vacuum pressure and the gas density in the collider. So taking all this into account, about 40 to 60 Kelvin has been chosen as the beam screen temperature for the FCCHH and also for the high energy LHeC. And with this optimized temperature, we still need 100 megawatt electrical power to cool away the 5 megawatt synchrotron radiation. So I think I'm almost done. I show a little bit on the civil engineering. If you're interested, we have a tool, tunneling optimization tool, which has been developed to optimize the location and the tilts and the position of the tunnel in the Ginevra region. This tool has been quite efficient and has been also donated to the ILC, and I believe it's used in the UK to optimize a bypass tunnel under the Stonehenge monument. So actually this tool has already several spin-off effects, but we have used it to optimize the location of the FCC tunnel. You can see it here. And then, as I said this morning, there are similar studies for the different locations in China. And actually the locations differ dramatically depending on the province and option, as you can see here. Some are have high mountain peaks and others are very flat. Also geology is very different. Then for the tunnel itself, the FCC tunnel has a 5.5 millimeter inner diameter. The lepton collider looks like this, rather small magnets. The collider is here with the twin aperture magnets, and the booster sits next to it. And then there is space for a transport vehicle. For the Hadron collider, we have this layout. This is a cryogenic line. This is the installed magnet, and then there's another magnet being transported around it. This is a Chinese tunnel, has a different shape, and it's slightly wider. It's 6 meter bottom width and has this layout which leaves maybe more space. And they have the Hadron collider at the left, and at the same time the lepton collider here, and the booster under the ceiling. For this construction schedule, we had an interchange with 2 consulting companies, and the result is as follows. Once we start the construction, after 4.5 years, the first sectors could be ready for technical installations, shown here. And the last sector can be ready after 6.5 or 7 years. So in total, we could finish this entire tunnel within 7 years or so, which is not too much longer than it took to build the lab tunnel. So then the overall schedule is like this. We assume that the next European strategy update in 2026 could make a decision to go ahead, and that 2 years later we could then start the civil engineering, and with these 7 years, and afterwards make an installation, and that would. In parallel, we have this magnet program that I mentioned earlier, and this is synchronized so that the magnets will be ready exactly when needed, and we could have, if we build the FCCHH directly, we could have first physics in PP in 2043. If we go for FCCE, we only need the tunnel, we don't have this magnet problem. We could be a little bit earlier and have first physics in 2039. And the high energy LHC depends on when HLHC stops. Assuming HLHC stops in long shutdown 5, we have to first remove the HLHC or the LHC and then install the high energy LHC in the tunnel. And then we could have first physics in 2040. This is the most optimistic technical schedule. And it's the starting point is set here by this decision in 26. So China doesn't have this constraint. They could have a decision next year or in 2 years, and then they are correspondingly earlier, 6-8 years earlier than us if they start earlier. We have this collaboration, by the way. Sorry, I noticed something to my surprise. Yeah, we have the worldwide collaboration. I don't know, earlier this year we had 124 institutes from 32 countries and 30 companies, and we have several EU-supported programs. I looked at the Italian institutes from these. To my surprise, Pisa is apparently not a member of the collaboration. It would be nice to have you on board. We have this, for example, this design study Eurocircle, which is designing the different magnets and also designing the Accelerator key components for the Hadron Collider. In addition to the core European countries, also CLIC is a member of this collaboration. We're very happy to have them on board. And we have recently, somewhat more recently, last year, we got this EasyTrain Marie Curie training network, which is developing the superconducting wire, a thin film technology for the cavities, and also other production methods for cavities and magnet cooling with these different institutes and companies as beneficiaries and partners. And this funds 15 early stage researchers over 3 years. So now we are producing the CDR. We are almost ready to release the summary volumes for the physics, Hadron Collider, Lepton Collider, and high energy LHC. And then there are 3 longer volumes which should be finalized next year. But these summary volumes are important for the European strategy. Also in China, already the conceptual design report was released early this month, 2nd of September. CEPC published the conceptual design report for the Chinese collider. Some few conclusions, maybe not so exciting, but anyway, FCC study, we develop high-performance energy frontier circular colliders for the post-LHC era as an input to the European strategy update 1920. There's this parallel effort in China, CEPC, SPPC, and I think the decision there could come within the next 2 or 5 years. There's a worldwide R&D programs on key technologies, now 3 tin superconductor, high-field magnets, also highly efficient superconducting RF systems. We have international collaboration, and I didn't go into detail because I have no time, but I think we have a nice stage strategy. We could start with the FCCE, and that gives us more time to develop the magnets for the Hadron Collider, and also share the cost and distribute the cost and time, then go to FCCHH, and we could afterwards combine several new ideas and use FCCE and FCCHH to make FCC mu and have a 100 TeV muon collider in the same tunnel. So I think that could be a nice collider program extending into the 22nd century. Thank you. Okay. Thank you very much.
Thank you. Questions? Comments?
I profit to ask a question. So can you comment on these high temperature superconducting magnets? I mean, you said that the main R&D program goes on in China, if I understood correctly. Is there something also, I mean, that could be done in Europe for if we choose to build the collider at CERN, for example, making maybe the ring smaller or not? Because I see that
there's some development on HTS already. LHeC is using some HTS links at the connection between the warm and cold temperatures at the feed boxes, and we are developing long cables for the so-called superconducting link to put the power converters further away from the magnets to put them on the surface. So these HTS cables are under development at CERN, but we don't, as far as I know, CERN is not looking at the iron-based HTS. We're looking at this bismuth and IPCO and more slightly older HTS materials. So I have not heard any very positive comments from our magnet group about this iron-based. I don't know if they are not too familiar or don't believe in it. But I went to a lecture from one of our magnet experts on HTS, and he didn't mention the material chosen by the Chinese in the entire lecture. So I don't know what it means, but
Can we
I think we should encourage IHAB to continue in this development, and there is a potential that they succeed. But it's not ready. Everybody believes that this is not ready in 2040. We cannot build 5,000 magnets in 2040 based on this technology. But maybe in 2060 it might be available, and that might be the right time if it comes after the lepton collider.
Thank you.
But we do a little bit. I think we will say this in our input. We will discuss this as a future R&D. And in some other European program, Lucio Rossi is developing also something in the HTS direction.
Okay, other questions? Okay, let's thank. Oh, one.
Thank you very much. Excellent presentation. I have very general questions. You showed us the World Atlas map with red points, FCC collaborating partners. I saw some countries in Middle East. May I know which countries are there? You showed us the map.
The map, yeah, yes.
Yes, with red points, FCC collaboration partners. And I saw some countries in Middle East. Turkey is there, Egypt, Iran.
Turkey, we have a lot. Israel is there, Turkey is there. We have a lot of institutes in Turkey.
Also Iran was there.
Iran is there, yeah. We have Iran as partner. And I think more Iranian institutes want to join. I have regular, yeah, they are a member of CMS. And sometimes they meet.
And Iraq?
Iraq, no, we have no contact to Iraq. Armenia is a member.
Okay. Thank you.
And we have some Russian, quite a number of Russian institutes. But everybody would be welcome. Yeah, we would welcome. We have also some Greek institutes. But
I'm originally from Switzerland.
You're originally from Iran?
I'm originally from Middle East.
From Middle East, yes. I have a fellow from Lebanon, but Lebanon is not a member. But I have a fellow from Lebanon working on FCC.
You have a FCC partner in Lebanon now?
No, just a person, just a Lebanese person who studied in France and then joined the FCC.
Sorry. I don't know if this is a stupid question, but the last slide made me think the idea of an FCC mu-mu. Why are there no other muon colliders being discussed and thought about? Is that, I mean, potentially it's a good compromise between electrons and hadrons. Am I wrong?
It's a good compromise, yeah, but I didn't understand completely your question.
So,
why are they discussed or not discussed? Or?
Why I haven't heard any discussion of it, and we haven't been discussing it in the last couple of days.
I think there's a talk here. No, there will be some talks later at this workshop.
Oh, okay.
But I think they were discussed. I think the US had a P5 committee, and they stopped a couple of years ago, maybe 2014 or so. They stopped the muon collider program in the US, and since then not much has happened. Now it comes back in Italy mainly. There's a new idea from Pantaleo Raimondi, and also Carlo Rubbia is pushing some other direction. But I think we should pursue. I think the new ideas are very good. We solved several problems. Maybe we could solve the problem of cooling. Maybe we don't need ionization cooling. And maybe we solve the production problem, but there are still some other problems. Actually, to accelerate the muons before they decay is also not so trivial. If you want to go to 100 TeV, it's actually quite challenging. So maybe we could use plasma acceleration to accelerate the muons to the high energy that we want. Maybe that could be a useful use of plasma first. So.
Thank you very much.
Okay, thank you. Thank you again from the speaker. So now, last lecture before the stop.
Okay, so before the coffee break, I will tell you about the detector options for the future proton-proton colliders. So this is what we have at the moment, the Large Hadron Collider. We have the 27-kilometer tunnel, 8.3 Tesla dipoles. So if you multiply the standard formula together, you come up with this 10.7 TeV, and because you cannot fill the full ring, you end up with 7 TeV. So the magnetic field and the ring is limiting this energy of the LHC. So if you look now at the the timeline, I mean, there were 1983 the first concepts, then 25 years later the first physics, and then another 25 years to the end of exploitation. So all these are huge programs, and if we want to think about the future beyond 2035, we have to start thinking now, and that's the whole purpose of this lecture series here. So, as Frank also showed, LHC, we have 8.3 Tesla dipoles in this 4-meter LHC tunnel, and to go to higher energies, we have to increase the magnetic field and also increase the tunnel. So for detectors at the moment, we have these 4 major detectors, Atlas CMS as general purpose detectors, and then the ARLIS specialized on heavy ion physics, and LHCb specialized on B physics, a forward experiment. So they have already significant sizes. These are a few pictures. So these are a few people standing between the big wheels of the Atlas detector. Here is the ARLIS detector at the end of installation in 2009 when we closed the doors. Here's some pictures from CMS when the tracker was installed, and this is some pictures from LHCb. So these have already quite significant size. So one of the iconic moments, of course, was the announcement of the Higgs boson in 2012, and this somehow has closed these open questions on the standard model, and there are many representations of the standard model. You can get it on t-shirts, on cups, and whatever. So this is, of course, a big success story. Of course, there's a curse with this, because if all the theory fits experiment, it's very hard to see where things are different or how to address the other questions. And I just compiled here something to motivate you to do experiments. So if you look at all the Nobel Prizes given for the standard model, there are 60 persons for experiments and instrumentation and 30 for theory. So especially because it's very hard to think about theories if you don't have any deviations from the standard model. It's extremely important that everybody is definitely looking into experiments and especially into instrumentation. So, you know, there were 3 people who got Nobel Prizes just for invention of a detector. That was for the cloud chamber, the bubble chamber, and the multi-wire proportional chamber. So if you want to become famous, okay, you don't have to become a theorist. You can also invent a marvelous detector such that you can afford these future experiments, because definitely in the near future we need technology to go the next step. FCC and so on, they're huge machines. We need very clever ideas to make all this affordable. So, what next? This is what this lecture series is all about. There is this idea of having a larger tunnel on the order of 100 kilometers, and specific for the Hadron option, there would be 16 Tesla magnets in a 100-kilometer tunnel, which gives a collision energy of 100 TeV. This is what Michelangelo already pointed out. I mean, there are 2 important aspects of what we want to do. One is there are known deviations from the standard model, okay? Dark matter, neutrino masses, baryon asymmetry in the universe. They're not accounted for in the standard model, and we try to get a clue on this. The other big priority is to explore the physics on the electroweak scale. So the question is the Higgs all there is at the TeV scale? What about the hierarchy problem and so on? So there are lots of precision measurements that have to be done on the electroweak scale in order to gain more insight there. And the whole FCC project is somehow focusing around these key points. So at the moment we are putting together all the results from this FCC study, and these 4 documents, one on the physics and then for all the machines, should be published within the next 2 months as an input to European strategy. So at the moment we are writing all this up. There is, as you have seen already, there is 1 tunnel, and this 1 tunnel could house either any plus and minus machine or a Hadron machine in whatever sequence we want. So to come a bit to the collision environment at such a machine, now if you go from how does this work? Oh la la. So if you go from 14 TeV at the LHC, okay, to 100 TeV, the total PP cross-section is rather flat, okay, that doesn't change a lot, but the cross-section for important processes involving heavy particles like top, double Higgs and so on is rising significantly, okay. So one good thing is if you go to high energy, the interesting stuff is sticking out more, that's a good thing. Of course, as we'll see later, we have a lot of pile-up, a lot of collisions at the same time, and this is again making our life difficult. But in principle, if you go to high energies, the interesting stuff is sticking out more, so that's an advantage. So, because accelerator people always have tables, I also tried to put together a table for experiment challenges, just to see how the challenges change between when going from the this is very difficult. So, when going from the LHC, high Lumi LHC, high energy LHC, or FCC HH, so in this first line, you see the related energies. So, all of them work at bunch spacings of 25 nanoseconds, and because the FCC HH has 30 times more luminosity than the nominal LHC, okay, and because the inelastic cross-section is fairly similar, what you see is that the pile-up becomes very significant, okay? At the moment at the LHC, there are about 30 collisions per bunch crossing, or because we're already working at twice the luminosity, it's 60. That will go to 140 at the high Lumi LHC. High energy LHC would be 500, and the FCC HH would be even 1,000, okay? So we have 1,000 proton collisions per bunch crossing, okay, at the same time. And that's, of course, a very serious difficulty in getting the physics out. You see, the luminous region is fairly similar for all of them. So the line pile-up density, okay, so in these many collisions, the distance between the vertices, it's at HLLHC on the order of 1 millimeter, and it becomes about only 150 micron for FCCHH, okay? So the average distance between individual vertices is only on the order of 150 microns, so to distinguish them is not easy. What you also see is that the charged particle multiplicity, the number of particles per unit of rapidity, it doesn't change a lot with energy. Also the number of charged tracks per collision, but because we have more luminosity, the total rate of tracks is of course higher. So at the moment at the LHC, you have about 60 gigahertz of charged tracks, and this will become 4 terahertz of charged tracks, okay? So you have 4 terahertz of charged particles being produced. Here you can also already get an idea on the data rate. If each of these tracks crosses, for instance, 20 silicon planes, and you have 5 bytes per track to store them, okay, that makes then already half a petabyte of data per second just from the tracker, okay, from this principle. Any sophisticated analysis of this will not get you closer to this. It's half a petabyte, that's the reality of what you have there. So that's a challenge for the data rate. Because we use a 4 Tesla field, you see that the bending radius of the average PT of produced particles is fairly similar. It's on the order of 50 centimeters. So most of the minimum bias tracks, they will just curl up inside the tracker. Then some numbers on radiation dose, which is important for the detectors. So the 1 MeV neutron equivalent fluence, okay, this is the damage number, especially for silicon. That's on the order of 2 times 10 to the 16 at the HLLHC, and this would increase almost by a factor 100, 50 to 100 when you go to FCCHH. So this is something where at the moment there are not really sensors that can survive this large radiation, okay? It's a factor 10 to 50 higher than what present silicon detectors can survive, so there's a lot of work to be done. One interesting thing here is also the energy that goes into the forward calorimeters. So this is the power that goes from primary particles to eta 5. At the moment, this is on the order of 0.2 kilowatt, but this would go to 4 kilowatt, okay? So if you have a calorimeter, finally, it will honor its name, okay? It's a calorimeter, it's heating up with 5 kilowatt. So if you use, for instance, cryogenics like liquid argon, that's quite tricky because you have to take away all this energy. So that's a very challenging number. What you also see here is if you go to higher energies, of course, a lot of physics is more boosted in the forward region. So, for instance, if you look at the Higgs to 4 leptons, you contain all the 4 leptons in time within eta 3.8 at LHC, but then at the FCCHH you have to increase your acceptance to about 5 in order to catch all the leptons. The same is true for VBF jets. You get 90% of them within eta 4.5 now, but at the FCCHH you have to increase your calorimetry to eta 6 to catch all of them. So you need very large forward acceptance in order to catch all the physics. So that's the last of these tables, just to show you the total rate of produced bees is 750 megahertz, okay? So there's no question on how to trigger on them. The only question is how many you can take on tape to analyze them. You have, for instance, 120 kilohertz just Z particles, and you have 10 kilohertz of top. Okay, so the rate of interesting physics is enormous, and of course that's why the challenge for trigger and data acquisition is big at this collider. What was mentioned already many times, the big challenge at future proton colliders is the pileup. At LHC, the nominal is 30 at this moment. At HLLHC, it will be 140. And at FCCHH, there will be 1,000 PP collisions at the same time, distributed in about 20 centimeter length. So the tricky thing is how, if you have tracks and events, you have to associate them to a primary vertex. The good thing is they don't happen exactly at the same time. There's a time spread of 10, 20, 30 picoseconds. So here you see an example from HLLHC. So all these events happen at slightly different times. It means if you have detectors that have time resolution on the order of 10, 20 picoseconds, you can actually start to distinguish some of them. So this high precision timing will be also a very important ingredient in future Hadron detectors. So now how to specify a detector for such a future machine? As we saw before, one question is exploration. Okay, we have to be sensitive to whatever new signals are there, but there is a lot of measurements to be done on the Higgs particle because it's somehow a tool or a portal to new discoveries. So I mean, the Atlas and CMS detector, they are general purpose detectors, and they were benchmarked with the Higgs that we didn't know the mass, so we scanned the mass of the Higgs particles, and tracking was up to eta 2.5. Now, since the Higgs is also a key benchmark for FCC detectors, and many features are highly forward boosted, we need to increase the acceptance. So if you want an FCC detector, has to be a general purpose detector with very large eta acceptance and also extreme granularity to deal with all the pileup. Okay? We don't know exactly what physics we look for, so we have to be open to whatever signatures. Here you see some of the things that I mentioned before. If the Higgs goes to 4 leptons, if you plot the rapidity of the highest rapidity lepton, you see there are many more forward-going leptons when you go from 13 to 100 TeV. And also here you see the VBF jets, they peak around eta 3.5 at LHC energies, and if you go to FCC energies, they peak around eta 5. So we need calorimetry even up to eta 6 in order to catch all of them. Okay? All this points to the need for increased acceptance in rapidity. Of course, with all this high energy, we can produce particles up to very high masses, and their decay products, for instance, if you have a 30 TeV C prime, you get 15 TeV tracks that you have to measure. So we have to be able to measure very high momentum particles. But because we also have to measure the Higgs and standard model processes that are at rather low PT, we also need a detector that is very good at low PT, okay? So it still has to be a very low material detector, such that also at low PT we can do very precise measurements. This is one more challenge that we have to deal with. For instance, if you look at a W from some, say, top decay, if these particles are at very high energy in the decay, of course the decay products are very close together. I mean, that goes under this heading of boosted objects. So you see that if the top goes to WB, the W and the B's, they are not going in opposite direction. They're very collimated. And for instance, at 10 TeV, the decay products are only within a delta R of 0.01. So it means you need very high granularity in order to be able to keep apart these very boosted objects. So that's also a big challenge on the granularity of these detectors. And here there's just then a list of specifications we worked out for this detector. So we want for 10 TeV tracks about 10 to 20% momentum resolution, and we want to stay below 1% at low PT. And for the calorimeters, we have specifications similar to what Atlas CMS have today. So 10% over root E for the E-cal and 50% over root E for the H-cal. So this was one detector concept that we came up with a few years ago. So this is a magnet coil, a solenoid with 6 Tesla and 12-meter bore. Okay, that's twice the size of the CMS magnet. And there are dipoles in the forward region to also measure the forward-going particles. And because a return yoke, a la CMS, would be too expensive for such a big object, there is the idea of having an active shielding coil that is shielding the magnetic field. Now, so if you want, this is a super CMS with 2 LHCBs sticking on both sides. Now, this went out of scale in cost and size. So there were some iterations on these ideas. So first we had this twin solenoid with dipoles. Then we said maybe it doesn't matter if the field lines go anywhere. So we removed the shield. Then we realized that even if in the forward region we don't have dipoles but solenoids, we still can have good forward acceptance and we keep the rotational symmetry. So in the end, we came up with this concept. That's the cross-section of our present reference detector. So there is a main solenoid here and a forward solenoid here, and this makes like a very long coil for very large tracking acceptance. Okay. You have then forward calorimetry, forward muon system, that's a bit a la LHCb, and this central system is a bit a la Atlas with the liquid argon calorimeter and the split of the barrel H-cal. And the muon stations are outside, but without any return yoke. Okay, the field lines, they can just go wherever they want. So that's, again, this concept. So we have a central tracker. We have 2 forward trackers in these forward solenoids. We have liquid argon electromagnetic calorimetry to deal with the radiation, the scintillator iron hadron calorimetry, and then outside we have the muon stations. Okay, this is a so-called reference detector that we use. The question whether there will be 2 or 3 detectors or whatever, this is something for later. This is just one detector concept that does the job and that we studied and parameterized to prove that we can do the physics at a future hadron collider. Now, if we have no shielding of the magnetic field, there's of course a big stray field. And this is why the service cavern is at a distance of about 50 meters from the main cavern. And you see that if you go to this distance, the stray field is below 5 millitesla. I mean, that's the limit below which you don't have to worry about your electronics. So with this distance here of 50 meters, we don't have any problem of stray field in the service cavern. The advantage is also if you leave 50 meters here, then the rock will hold all these structures. If you move this closer, you have to start to build concrete pillars here and so on, like in Atlas or CMS. But with this distance, you can just have 2 independent caverns. It's also cheaper for civil engineering. The fact that you have more length for the services, I mean, we went through the list of issues, but that doesn't seem to be a decisive factor. So these are the magnet configurations of this detector we investigate. One is, as I said, a central and 2 forward solenoids. We still study for the CDR the option where we have dipoles in the forward region, just to see how much improvement we get in tracking in this case. Of course, these dipoles, they also have influence on the beam of the machine, so there have to be compensation schemes and so on. You lose a rotational symmetry, so it's not an easy magnetic field system, and only if there's a very important advantage we would think of going this way. Otherwise, we keep the first option with all the solenoid field. This is just a comparison of this detector concept with Atlas and CMS. So you see it's even a bit smaller than Atlas, a bit larger than CMS. So it means it might be possible for the 100 TeV collider that we stay on a similar scale with our detectors. We don't have to increase them by big factors. This is just a comparison to LHCb and ALICE, just to show that I think it's possible to build detectors on a scale that don't go much beyond what we have at LHC at the moment. This is just to give you an idea on the infrastructure. So the last objects of the machine are these final focusing quadrupoles, and they are at a distance of 40 meters from the interaction point. Okay, that's the so-called L star number. So then there's a shielding and some other shields. So the good thing is that all this stuff is in the tunnel. We don't have to deal with it, and we don't have machine elements in the cavern. We just have our detector. Okay, this is a big advantage. If you compare to E plus, E minus, okay, there the final focusing magnet is not 40 meters away, but 2 meters away from the interaction point. Okay, the magnets are really sticking inside your detector. So that's why this machine detector interface is a highly complex question for an E plus, E minus experiment. But for the Hadron machine, these final focusing magnets are far away. So that's a good thing. So just as a comparison, the present Atlas cavern, it has a height of 35 meters, width of 30 meters, and 50 meter long, shaft of 18 meters. So if you just take the Atlas cavern and make it 20 meters longer, you could already house an FCC detector. So the scale is similar to LHC detectors. Here are some numbers to show you the charged particle rates. So that's at the peak luminosity of the FCC HH. And what you get there is you have about 12 gigahertz per square centimeter in the first layer of the silicon. So that's very tricky to get all this data out of your detector. And the outer layers of this tracker, there you go to a bit more moderate levels, but still quite high. What is good to see is that with all these shielding arrangements in the Muon systems, we have rates on the order of 500 hertz per square centimeter. And this is not so different of what we have at the LHC at the moment. Okay, so it means that, I mean, if you look at HLLHC, in the Atlas barrel system, you have about 0.3 kilohertz per square centimeter. In the forward region, 10 kilohertz per square centimeter. So it means in the entire Muon system, except the very forward part, we can use technology that is available already at the LHC. So for the Muon systems, it's large, but the technology that we have in hand should work there. Now that's different for the trackers. So in terms of radiation load, as I said before, the first silicon layers and also the very forward ones here, they are from the order of 6 × 10⁻17 hadrons per square centimeter during the lifetime of this machine. And that's really like 50-100 times more than what present silicon detectors can survive. So there is a lot of R&D needed to have new sensors. You see here also very well where all this radiation is coming from. In this forward calorimeter, okay, you have a lot of particles being absorbed there. And in these shower processes, you produce lots and lots of neutrons. And these neutrons, I mean, this becomes, they moderate in there. This becomes like a diffuse neutron source. And this is entering the entire cavity of the tracker and producing all this radiation. But there's no way out of it. I mean, you cannot put material in front of the calorimeter to shield it, okay? There's no choice there, so that's a reality. Now, at the present LHC, the way to deal with it is, I mean, for instance, in Atlas, you see the forward calorimetry is not far away. It's actually closing inside the end cap calorimeter, so all the neutrons, they stay inside here. In CMS, I mean, there's an opening to the forward, but the forward calorimetry is then closing up together with this muon system, so that's also why these neutrons, they don't get out. But if for the future, for this FCC detector, we want to move these tracking systems in calorimeter very forward, we have to make this massive shielding all around in order to make sure all these neutrons don't escape to the muon system. And this is why we have such a big shielding here, such that all the neutrons that are produced in the forward calorimetry, they don't come out into the cavern. So that's an important element of such a detector concept. Okay, a few things about tracking. These are just, as a reference, some formulas, and it's always amazing when you go through the full simulation, these formulas are always very close. So they are a good thing to have to check if simulation makes sense. So, and we, as I said before, we studied two magnetic field systems. One is a central solenoid with a forward solenoid, and the other is the central solenoid with a forward dipole. Okay, here is the dipole field where you bend the particles left and right. So this is the performance with this magnet system of our tracker layout. So you see, for the highest, I mean, this is now the momentum resolution versus rapidity. So we managed to get about 20% momentum resolution for the 10 TeV particles, and the multiple scattering limit is on the order of 0.5% with the material we assumed. Now, if you go more forward, at some point here, you enter this region where you lose a bit of lever arm, so the resolution gets worse, but then the particles enter the forward solenoid, and this is where, again, you recover your momentum resolution, and only on the very forward region here, the resolution then gets worse. What you see, the dashed lines here are what you would get with the forward dipole. So you see, in principle, for the low momentum particles, one could manage to stay below 1% momentum resolution all the way up to eta 6 if we have a forward dipole. But the question is, of course, the question is how important this is. So the question whether this dipole is a good or important option depends on all the detailed studies that we have to do. Here you see the layout of the tracker in a very distorted way. The full length is this 32 meter of our detector, and the radius is about 1.6 meters. You see, what's very popular at the moment is to have inclined modules, because then you see this here. If you incline your layers, then a particle passing your layer is passing perpendicular, so you have less material, less multiple scattering, and that makes it easier to do pattern recognition, and you also save a lot of silicon surface. So that's the layout of the tracker. What you see with respect to this pileup that I showed before is the following. What happens is you have many pile-up vertices, and you have a track coming from one vertex, and then it goes through the beam pipe, and then you have a certain resolution of your tracking layers. Now, if you imagine that your detector is perfect, okay, if you have infinite resolution in your tracking, you still have scattering in the beam pipe alone, and what you see is just from the beam pipe, okay, if you go to an angle, to an eta value of if you go to an eta value of about 2.5, only the scattering in the beam pipe already confuses different vertices. That's because the vertices are so close together that you cannot resolve them. So there is some limit from the beam pipe itself on the vertex resolution, even if your detector is perfect. So it means that there will be the need for precision timing in order to reduce this pile-up effect. This is just some number shown here called effective pileup. So what this is if, for instance, you have a track of a given momentum at a given eta, okay, if you have no timing, okay, you confuse your track with about 10 vertices, and if you have timing on the level of 25 or even 5 picoseconds, then you can identify the vertex with very high probability. So this is just to show you that high precision timing, not only at LHeC, but especially at FCCHH, will play a very crucial role. So for calorimetry, just to quickly show you, we have liquid argon electromagnetic calorimetry here because it's intrinsically radiation hard. At this moment, there are no crystals that could survive a Hadron, one of these future Hadron machines. We study as one other option something a la CMS, where we have silicon in the calorimetry as an option, but the reference is liquid argon. And then for the Hadron calorimeter, there the radiation levels are really much lower, so there we can use something very similar to Atlas or even CMS, so it's just iron and scintillators. And then, as I said before, the Muon stations, there we can use standard technology that we have also at the LHeC. Here are some performance numbers from the liquid argon calorimeter. So it's different from the present Atlas design, where there is this harmonica design. Here it's just inclined plates, and that allows to have much higher granularity. Because of all this pileup and all these boosted objects, we need about 10 times more granularity as compared to Atlas. And from the simulations, we can, with such a geometry, achieve the performance numbers, so about 10% over root E with a rather small constant term. Here you see the invariant mass peak of the Higgs particle at 0 pileup and then at pileup of 1000. So you see, because of all this pileup, all these tracks that go into your calorimeter, of course the resolution deteriorates, but that's not the final word on this, because you can use all these tracks that you also see in the tracker and subtract this energy. So we think that at the pileup 1000 one can significantly improve this resolution by doing corrections with tracking, but this is still a study to be done. For the Hadron calorimeter, as I said, this is similar to what is used at Atlas. It's steel plates, some lead in order to make it more compact, with scintillator and silicon PM readout, and that gives the possibility of a very granular H-cal, and the total calorimeter depth we assume 11 lambda in order to contain the highest energy jets. For muon systems, there are 3 ways we can measure the muon momentum. One is, if this in red would be the tracker, in blue and yellow the calorimeter, and then you have the muon system here. You can either just measure the muon in your tracker and then use the muon system here to identify it as a muon, or you just measure it in the muon system, but just looking at the track under which it comes out of the calorimeter, or you make a combined measurement. These are the 3 possibilities you have. Here you have some basic formulas for this for reference, and that's what you get. So if this is now the muon momentum resolution versus muon energy, if you have the tracker only, then from a certain momentum, of course, you deteriorate because the lever arm disappears. If you measure only in the muon system, you never get to 0.5%. You stay at about 5, 6, 7% because of the multiple scattering in the calorimeter. I think in CMS this number is on the order of 9, 10%. But then if you combine the muon momentum measurement, the muon system measurement with the tracker, you see that even up to, these are numbers of like 20 TeV, you can still get below 10% because you have such a large lever arm here. So if you measure the muon here together with the tracker with this long lever arm, you can get a very good momentum resolution. Okay, so these are the concepts for measuring the muons, and this is just if you versus eta, of course in the forward region you lose bending power, and this is why the muon momentum resolution decays as you go to forward, the more forward region. There's also a number that is very similar to what CMS has at this moment. Okay, and finally, just a few words on all this data rate and on trigger and duck. So just as a reference, if you look at the present Atlas detector, for the phase 2, for instance, the Atlas calorimetry will be digitized at the full 40 megahertz, and all the data are sent via optical links to the level 1 trigger. So that's about 25 terabytes per second, okay? This was inconceivable at the start of LHC because, I mean, the power for these ADCs was way too high, so there was no way to cool it, but now it's possible to digitize that, and that gives about 25 terabytes per second. So if we take our FCC detector, okay, and if we say that we read all the calorimeter channels at this rate, we get about 10 times more, okay, 200 to 300 terabytes per second. But this doesn't seem insane, okay? On the time scale of 20 years, this will be possible. So we assume that we can definitely push all the data from the calorimeter and muon system via fibers to some high-level trigger farm. Now, whether it's possible to also read the tracker at 40 megahertz, okay, these 800 terabytes per second, this has to be seen because all these links need a lot of material, a lot of power, and that can completely screw up the tracker performance. So what we are studying is just to see if we have all the calorimeter and muon system performance available, whether we can devise a trigger to reduce maybe the tracker readout rate to about 1 megahertz, like it's the plan for HLHC. But it could also be that we have technology to just read everything, but that has to be seen. So as a reference for Atlas and CMS at HLHC, there will be a level 1 trigger with about 100 megahertz rate, and at 1 megahertz the data go into the high-level trigger computing farm. So there's still a factor of 40 of hardware trigger for data reduction. Now, what LHCb and ALICE will do already now after LS2 is to not have any hardware trigger. Okay, there all the data are digitized and pushed at 40 megahertz into a high-level trigger farm. In LHCb, there will be still a trigger, but in ALICE, there is online reconstruction, and then even all data will go to permanent storage. Of course, channel numbers are smaller than Atlas CMS. That's why it's possible there. But this is already on the path to this idea of just having a triggerless system. You read everything into an HLT to be able to do either software trigger or just data reduction. There's one reference. I mean, all this depends, of course, on computing power availability. So there's somebody who says if doubling computing power every 2 years continues, then in 2030, whatever technology we're using, then it will be sufficiently small that all the computing power that's in a human brain can also fit in the physical size of the human brain. And this professor here says that this is when artificial intelligence starts to take over. And this is a good thing for us because the HLT, we send the data in and then the papers come out themselves. Okay, we don't even have to think about data analysis. It's good. Okay, there's a lot of strategic R&D that we need, of course, for arriving at detector sensors for such a future machine. Of course, at the moment, all the R&D is driven by the phase 2 upgrades of Atlas and CMS and also ALICE LHCb. But beyond that, we have to put in place, and that's done by CERN, a strategic R&D plan in order to develop technologies further towards these future machines. Okay, so that brings me to my summary. So, as I showed, we are studying a detector for a 100 TeV Hadron Collider with 100 kilometer circumference. Peak luminosity is about 10 to the 34, and that means a pileup of 1,000. That's the key challenge. And the other key challenge is that we have enormous radiation levels that have to be survived by the detector. I think we conclude that it seems feasible that one can build a detector that fully exploits the physics potential of such a future machine. But of course, we need a high-profile R&D program in order to develop electronics and sensors that can survive all this radiation. Okay, thank you.
Thank you. So thank you for the interesting overview of our next life. Questions?
No, curiosity more than a question. Any idea about how to build the inner tracker for the detector?
Well, so the two key problems. One is the radiation hardness. Okay, this refers to the first 20 centimeters. So if you go more than 20 centimeters, then the technology of HLHC is already okay. Okay, so the question is for the inner 20 centimeters. That has to be solved, and the other question is how to deal with this high data rate of the very inner layers, because you saw this 10 gigahertz per square centimeter, that's the difficulty. So I would say beyond a radius of 20 centimeters, okay, it's fairly clear how one would build a tracker. Inside the first 20 centimeters, that's very tricky. I mean, there are some people who think that it will be difficult with silicon, so they call this a Kleenex detector, where you throw it away every month. I mean, you build many of them. That's the trivial option. But okay, this has to be studied. Okay, that's for all of you guys to figure out.
Other questions? Comments? Okay, thank you again. Thanks. Now there is short coffee break.
Yeah, for the coffee break you follow Simone and you make quite a tour on. So, again, good afternoon. After this very nice lecture on FCC and on Very Future Collider, we change field, and we have a keynote talk by Professor Antonino Cattaneo, who is the director of the Biolab at Scuola Normale. Actually, he did his PhD at Scuola Normale with Lamberto Maffei, and later he worked with Rita Levi-Montalcini. He was one of the founding fathers of the European Brain Research Institute, that he acted there as scientific director. And then he moved to CISA. He started the neuroscience program at CISA, and since 2009 he's full professor here. And he has been kind enough to give this talk where he will tell us how do we write in our brain. That is one very fascinating topic. Thank you, Antonino.
Thank you, Gigi, for the opportunity. Good afternoon to everyone. So when Gigi Rolandi asked me to talk in front of this audience, I was and I am quite scared, because what I'm doing is very different from what you are doing, and I have a huge respect of the problems that you are dealing with. So I'll try to take you through a detour of how, as Gigi said very, very, very nicely and synthetically, how what technology the brain uses to write into our nerve cells, nerve circuits, when we learn and remember something, and how these memories are read. So it is actually a question of a biological strategy that the brain uses to write, read, and erase facts and aspects of our memory. I will take a very, I'm a wet neuroscientist, so I deal with real neurons, and I will take you through a detour that will try to take you from basic principles to the newest things that we are doing in the field. If I have time, I will try to take you to the current frontier. This is not to say that there are no close links between neurosciences and physics. I will talk you about the biology of how memories are written and read, but over the years and the decades, neuroscience and physics have been a very fertile cross-reacting fields. Both deal with frontiers of our mankind thoughts, and just this is now taken very seriously, And the brain can be studied at many different levels, from the molecules to synapses to nerve cells to circuits to brain areas to the whole brain cognitive aspects. And all these aspects, there are methodological aspects and there are conceptual aspects that in which some different thinking, such as that the physics can bring, are deeply required. As I was saying, this is taken now very seriously. There is this large European project, that is this European Human Brain Project, flagship project. Is a 10 years project, which is very, very deep involved, involving physics. So this is just also a hook that I give to young students. There is a big need for the training and recruitment of a new generation of neuroscientists that come from hard physics, because the aims of this project are, in which Scuola Normale is involved. We are actively participating in the project, and the aim of the project is to use biological data to draw simulations of at different scales across the brain, and how to use these models to then make predictions that experimenters can test in a very, very positive feedback way. And I heard in the previous lecture, at the end of the previous lecture, that mention was made by the need for increasing computing power in your discipline as in many other disciplines, and one of the aims of the Human Brain Project is, in fact, not only that of simulating the brain, but also the converse, is what we can learn from the brain, the computational strategies that the brain is using to design new, as they are called, neuromorphic computing strategies that can be used for hard computing in other disciplines that are not studying the brain. So neuromorphic computing is one strategic direction of the Human Brain Project. Now, let's come to my talk. I will deal with memory. Actually, memories. There are many different types of memories. I won't go into this. We have motor memory, episodic memory, semantic memory. You know emotional memories. You know yourself what type of memories we have. So memory can be studied at two different levels, at least. One is how information is represented, where and how, in which brain areas. I will not deal with this today. The second aspect is what common mechanisms at the molecular and cellular level are used by the brain in these different forms of memory to store, write, and so memory processes are basically the general subject of our mind. This has been recognized through the centuries by philosophers, by poets, by writers. You all know about, and I think that Dante, in this famous verse, states it very briefly and synthetically. You cannot, if you perceive without remembering, you cannot have knowledge. This is said in beautiful poetic terms, but this is the essence of what memory is. Philosophers have a reason that memory is our personal identity. Locke is the champion of this view. We know who we are and what we are because we have a sparse sampling of our own life. So memory and identity is. So we are not dealing with this. What we are dealing today is actually. There is another reason why there is a big interest in studying memory. That is not only understanding and the physiology of memory, but is the pathology of memory. We all know that with the growing age of our societies, there is a huge need to understand and to cope with this severe disease. And the message that I want to give is that despite decades of intense research worldwide and the massive investment, we still don't have a cure and an early diagnosis for this disease. And so this is an additional reason. For someone may be the prime reason, for others may be an additional reason to study the process of memory. And one point that I would like to make in my talk today is that so far this disease, I will not be talking about Alzheimer's today, but I want to make a point that in decades Alzheimer's disease has been studied in a very reasonable way by starting from the endpoint targets. There are crucial molecules that are involved in how neurons die in this disease. These proteins are so-called tau tangles and amyloid plaques. They are made from normal proteins that go wrong in the disease. And that's a good starting point to to climb over the causes of the disease, and all therapeutic approaches currently are being targeting these molecules, and despite this, there is a disappointing sequence of failures. We still have currently drugs that are the result of the research in the 90s, and also the drugs that are a new generation of drugs have failed, and it's long, we can discuss it for long, but the reason is that we probably need to tackle this disease not starting from the endpoint, but starting from the fundamentals of memory. So this is, I want to, having studied and still studying this disease currently in the lab, this is why we ourselves, we took in recent years the growing list of groups who are studying the mechanism of memory from a fundamental point of view. So there is a gap here, a mechanistic gap between Alzheimer's disease and studies of memory. So here there is Raffaello's Scuola di Atene, in which you see Plato and Aristotle, and these two philosophers were amongst those who reasoned by reasoning into a black box, as philosophers do, that there is something that is written in, they didn't know that it was the brain, but we now say in the brain, when we remember something, and this is what they called the famous metaphor of a wax tablet that in which you write something, to grammateon. So Cartesio, over, just to name one, reasoned about the fact that when we learn and remember something, there are some pores in the brain, I would say now, in which some fluid, we now know that this is electricity, modulate the opening of pores that is facilitated when we learn and remember something. In modern terms, this is synaptic plasticity, what I will describe to you now. So the point that I want to make is that the thinking of philosophers have prepared our minds, the minds of scientists, into studying this process. And it was in the early previous century that a neuropsychologist, Richard Simon, coined a word that is now very much used, that is the engram. The engram is what has been written when we learn and remember something. And this, the search of the engram is what those who study memory now are looking for. What is the engram? What is, how can we manipulate it? How can we recognize it? How can we use it to understand how we form memories? And in the 50s, this was still an intractable problem. The search of the engram was considered, basically, this is an example of a systematic study in which Lashley, a famous neuroscientist of those years, concluded that his pursuit in search of the engram was negative, and that the real nature of the engram was probably something that could not be studied with technologies of the time. It was really a question of how you can, you have experimental techniques and knowledge to zoom in to recognize these engrams. So what we now know is that the idea is that an engram is an assembly of cells whose activation occurs when we learn something. They store this pattern of activity, and that this can be recalled when we remember. So the question is, we have now to think of this idea of a sparse combination of neurons in a relevant area. I told you I will not mention which area for what memory. There is hippocampus for episodic memory, cerebellum for motor memory, etc., etc. But this is not, there is a common idea that you have a set of cells that are activated, and these cells, this combination of cells in a sort of combinatorial code, is what encodes a particular information that corresponds to the memory that you are recalling. The trace itself is dynamic, so you first store this memory in the hippocampus, and after weeks there is evidence that this goes to the cortex. This again is these details that are not needed now. What can we say about how this activation of neurons is formed? So, the paradigm, again, is set by an old landmark study. Those of you who use neural networks for computational problems, pattern recognition, and other things like, certainly know the Hebbian learning rule. Hebbian learning rule comes from Donald Hebb, a neuropsychologist of the 40s and 50s, that on purely theoretical and conceptual grounds postulated that neurons that fire together wire together. There is a coincidence of activity between a presynaptic neuron and the postsynaptic neuron, and if there is this coincidence of activity, that connection will be strengthened. And this was a very landmark intuition, and this has proven true and very fruitful prediction over the years, and I will show you an example of this. So basically, over the years now we reach, we make a big jump and we reach the early 2000s, in which we now have what is called the synaptic plasticity paradigm. A synaptic plasticity paradigm posits that at a synapse, where you have neurotransmitter that is released in an activity-dependent way from the presynapse to the postsynapse, that is, this is a postsynaptic neuron, you have this chemical neurotransmitter that is released and that acts on postsynaptic receptors. So the transmission in the brain is not purely electrical, but is electrical coupled to a discontinuity that is then chemical. One can wonder, this poses a big constraint on it's a slowing step. This one is a big slowing step. There is a price to be paid, but there are huge advantages to be gained by the fact that the communication is not purely electrical, and the huge advantage is that the brain is not an electrical device. The brain is a device, if we can call it this, activates processes that combines electrical signaling with slow molecular chemical machinery, and this you will see exactly how and so this chemical step of the synapse offers the opportunity to a huge and multi-level integration and regulation of how the synapse can be weakened, strengthened, or changed in a short or long-lasting way. So this synaptic plasticity has developed by studying simple model systems. You all know, probably have heard about Eric Kandel's study of the aplysia brain, which is a small mollusk with a few number of neurons with respect to the human brain, but I will not dwell with this. In the human brain, in the mammalian brain, a phenomenon that has been very much studied is what is called long-term potentiation. This is an example of an experiment that is widely used to study the mechanism that I will now want to describe to you. And so this is a mechanism whereby you stimulate a synapse that in the hippocampus in this case with an electrode that the green axon stimulates this CA1 postsynaptic neuron. So this is the synapse that we are stimulating, and if you stimulate it you have this trace here. This is measuring the current, the potential change as a function of time in response to the stimulation of the green synapse. And if you repeat this stimulation at a test stimulus, you always get this response. But when you do something to the synapse, you strongly stimulate it for a short while, and then you go back to the test stimulus, then now the response is changed and is a much wider response. And this is not transient. This can be made permanent. So this is the basis of a phenomenon that is called long-term potentiation, because that synapse is changed, we can say, forever over the time scales that are of interest to our experiment. And you can see this here you have the responses to the test stimulus. You repeat this response. You have the change of the synaptic efficacy as a function of time. You see this response is very consistent. Then you do this, what is called high frequency stimulation, is a boost, a stronger stimulus. So you have you have an increased response to the same test stimulus, but then the response stays on. And this stays on for, you can measure it, stays on for weeks. It's really a long-term facilitation. So something has happened to that synapse in the context of a circuit because of the result of this transient stimulation. Of course, this has nothing to do with me remembering the face of my children. It is a reductionist phenomenon, but it is a phenomenon that has allowed to understand very much about this. And what is that as a function of the stimulus that you give here, this change can be transient or can be permanent. So there is something that happens here when you give this stimulus, and here are the responses always to the same test stimulus. And so the mechanism of this, there is a concept that I would like to make, is the fact that when a synapse changes its efficacy, means that you have a test stimulus and it changes its response, it means this change is implemented by molecules in the synapse that have changed. So the protein composition of the synapse has changed. So this is the link between electrical phenomena that you're measuring and molecules that are there. So how is the composition of the synapse controlled? Because when you have a long-lasting change, this means that the composition of the synapse has changed. And so another thing that you must keep in mind is that all proteins have a constant turnover. So the half-life of proteins is much, much, much shorter than the lifetime of the synaptic efficacy. So this has been a question that has bothered the neuroscientists for decades, how you can implement a long-standing change, long-lasting change, with rapidly turning over molecules. And so it turns out, well, before going into this it will be a crucial question in my talk. Before going to this, let me show you an example of how a Hebbian mechanism works in the plasticity. This is a synapse that uses glutamate as a neurotransmitter. This glutamate has two types of receptors. These receptors glutamate is the key that opens some locks, and the locks are the receptors. And when this glutamate binds to these receptors, the receptors let some ions flow in and the membrane depolarizes and the postsynaptic neuron is activated. So there is one type of receptor that is the blue receptor. I won't give you the name, that is irrelevant for you now. And this receptor responds when glutamate binds to it and it depolarizes the neuron. Then you have this pink receptor. It is the crucial point at these synapses. This is a conditional end detector. This receptor is normally blocked at the membrane potentials in which this membrane is normally found when it is not activated. So this block is unblocked when the membrane potential is depolarized, so is activated. So you need a small step of activity induced by this one in order to unblock this. But then what? So this detects the coincidence of glutamate and of a membrane depolarization. And who provides the membrane polarization can be an endless amount of mechanisms. So really this is a Hebbian mechanism that says that when there is a coincident activity between the presynaptic and the postsynaptic neuron, then the synapse gets activated, because it is the activation of these pink receptors that are then involved in the long-term potentiation, because the pink receptors, NMDA receptor they are called. So for some of you who want to know about this, this is a famous NMDA receptor. It leads to an influx of calcium, and this calcium makes lots of things in the postsynaptic neuron. So it is this particular ion that enters this receptor and not this one that then triggers the long-lasting receptors. So now, this is a Hebbian mechanism, a coincident mechanism. How then can this lead to long-lasting events in face of rapidly turning over processes? Because the short-term facilitation is implemented by proteins that are already there. But when the stimulus is no more present, that synapse remains facilitated. These pink receptors remain activated, even if there is no... So something has changed irreversibly for our purposes to that synapse. And so the important point is that there is an important biological mechanism that can make long-lasting changes to a neuron. And this is gene expression. This calls heavily DNA into the mechanism of how neurons work. Because changes in gene expression are the mechanism how, in our body, we translate short-term stimuli into irreversible changes. When our body develops during embryonic development, we have a process that is called differentiation. A muscle becomes a muscle, a nerve becomes a nerve, a blood cell becomes a blood cell. We all have the same genes, but a muscle cell, a nerve cell, and a blood cell differ by the genes that they express, by the RNA that they produce. So these are irreversible changes, and it has been a crucial point to understand that when a nerve cell learns, with quotation marks, when a nerve cell undergoes these long-lasting changes, what are called into action are no more electrical phenomena, but are phenomena that involve its DNA. So the DNA of a neuron is crucially involved in allowing the long-lasting changes that occur at the synapse. And the DNA changes are occurring in the nucleus of the soma of the neuron, and the synapses are in the periphery of the neuron. So there is this long-range communication between synapses and nucleus. And this is one experiment in which you show that if you give an inhibitor of the synthesis, protein synthesis, or of RNA synthesis, only during the stimulation that leads to the long-term potentiation, you abolish it. You don't abolish the short-term, because that is implemented by proteins that are already there. But you block the long-term maintenance. So you need transcription, that is the process that makes from a gene to an RNA, and then you block translation, that is the process that from an RNA makes a protein. Interestingly, if you give this inhibitor sometimes later, you don't inhibit the process. But that's a complication that we can discuss for those of you who... So, you need new gene expression to support long-term synaptic changes. So, these are different synapses that are impinging on this postsynaptic neuron. This, what I told you, implies that when you have this synapse that is activated, but not this one, you have some signals, meaning molecules, or signals of some sort that travel to the soma, to the nucleus, where you have DNA, and as a result of this, DNA makes some new RNA that then makes some protein that travels back and act what is called plasticity products, and this acts on this synapse to stabilize it. So, the short-term to long-term transition of synaptic plasticity involves a close molecular dialogue between synapses and nucleus. And this is very well understood now and characterized in many different examples. You can use this because the corollary of this is that a neuron that has been activated transcribes some new RNA. So now you have a molecular handle to see in a brain. You give a stimulus and you make, for instance, a learning training in some learning paradigm. You can watch the neurons that have undergone the training by watching which cells are making these what are called immediate early genes, that are a set of genes that are involved in the synapse to nucleus communication. And so an example of this is given here, in which you can do actually an experiment in which you can see these pink, this green, the pink are the nuclei of the neurons, and the green dots are the transcription of this RNA molecule that is activated by synapses that this neuron is made. And so when you take a mouse and you put it in a spatial context that is called A, you activate these neurons, this combination of neurons, these are that are defined here, and then this RNA starts going out of the nucleus. So half an hour later, you can recognize the neurons that had been labeled half an hour before. So you have 2 time points in which you can identify which neurons are expressed At the first time, in a first stimulus and in a second stimulus. And you can see that if you put a mouse in one context and then you put it back again in the same one, there is a coincidence of this stimulation. When you put it first in A and then in a B spatial context, different neurons are activated. So this gives you 2 time points to do what is called activity mapping. This is the first molecular handle that has been used over the years. It's still correlation. Now I want to take you to a step where we can interfere with the process. Now there is a complication. That everything that I told you, I said that there is a dialogue between synapse and nucleus. And in one of the drawings, I had 2 adjacent synapses, one of which was stimulated and the neighboring one was not. And I I have hidden the problem. The problem is here that you potentiate one synapse if that one is stimulated, and you don't stimulate and you don't facilitate the neighboring one, even if they belong to the same neuron. So there is what is called synapse specificity in the potentiation. Yet, the nucleus is the same for all the thousands or tens of thousands synapses of the same neuron. So here you have a problem of a huge complexity. How is a signal that is transferred from one synapse to a nucleus that is in common with all the synapses of a nucleus, how does it act specifically on that synapse? So you have a big specificity, the so-called problem of synapse specificity. The solution of this came to a very ingenious trick that normally protein synthesis is occurring in the soma. So RNAs are made on the DNA that are in the nucleus, and then the RNA exits the nucleus, and there are ribosomes that make protein. And then proteins travel. But you need protein needs to know that they need to act on this synapse and not on this one. It is difficult to think such a mechanism. So the solution of the neuron is the following, that a large majority of the RNA molecules that are transcribed in the nucleus in response to the synaptic activation of one of its synapses do not make protein in the soma, but travel as RNAs. Repressed, translationally repressed. And they travel everywhere in a non-specific way to all the synapses of a neuron. And it is only at the synapses that had been activated that a tag had been set. Now, I won't go into what is this tag. That lasts a few hours. It's a so-called of molecular memory that waits the time for the signal to travel this way and come back, that allows that RNA here, but not here, to be translated and made into protein. So this is how a signal that is activated by a stimulated synapse can travel back to the nucleus, induce transcription, and then the RNA goes back everywhere in the neuron, but it only makes protein, that is what functions, at the synapse that needed that. And of course, you need to postulate that here there is a molecular tag that lasts for the few hours that are needed for this. What is it? We shall use a tag at the end of the talk. Okay. Now we are set, more or less. This is picture that is how we think now that cell assemblies that are activated as a result of a certain learning, training protocol. We use, as I will show you, simple training protocols in the mouse. For instance, a fear conditioning is something that I will tell you something about. And so now we can use what we have learned so far to ask 2 very simple but fundamental questions: necessity and sufficiency. So can we prove that a certain combination of activated neurons are necessary for a certain memory? In order to address this question, we need to be able to identify these neurons and do something to them, but only to them, to kill them or to inactivate them or to silence them. And then the readout is the memory preserved or not? And the sufficiency question is a harder one. The sufficiency question posits that if I have identified a set of candidate neurons that have been that correlatively I can show to be activated in a certain learning task. Can I reactivate them artificially in the absence of the trigger that would have activated the memory? And would this reactivate the memory? That would prove that the activation of these neurons is sufficient to support a certain memory. So this is what we are able to do now. And in order to do this, we need to genetically tag the neurons active during a learning task. And then we need to use this genetic tagging to drive the expression of a protein that is an artificial protein that will either silence those neurons or reactivate them during a certain time window.
May I ask a question?
Of course.
Regarding the synapse specificity that you referred to, as I understood, it's coming from transcription process from gene to RNA and from DNA. Is that it is the information is embedded in DNA?
Yes, an RNA made from
Can I
DNA.
say this synapse specificity is really specific for the person?
No. This is not specific. The spatial scale here is the scale of a single neuron down to its thousands of synapses. So the specificity is not a specificity of an individual. It's a specificity of that synapse in that neuron. We are the scale at which we are doing this is the spatial scale of a neuron and smaller of its synapses. So when I say synapse specificity, I talk about one synapse versus the neighboring synapse of the same neuron.
This is not dependent on information in DNA?
It is dependent on the information of the DNA of that neuron. I'll come back to this. So we need now to do these two things. How can I genetically tag neurons that are active during a learning task? So this exploits what we have said so far. I told you earlier that when you stimulate synapses, you have genes whose expression is turned on. Expression means they make RNA. And so these are immediate early genes. So seems complicated, but I will take you through. It's very simple. Every gene makes RNA when its coding region, the RNA, is downstream of a sequence that is called the promoter that decides when to be active. So this promoter is active when the synapse of that neuron is active. So I place what people have done with this manipulation is you place a promoter of a gene that is active during synaptic activity, and you put downstream of this an effector gene that turns on in response to a certain chemical the activation of a colored reporter. So when you remove this drug, you turn on this promoter. So this is a way, with some complications, of opening a window of opportunity when you remove the drug. This is now done at the level of the whole animal. You take the drug off and you give a stimulation. For instance, you train the mouse to a certain spatial context like this Sala Azzurra. And when you place this mouse in the spatial context in the absence of this drug, this mouse becomes red. So during that period, you label those neurons that were activated by learning this context. And they become red. Now this can be a color, but can be now a toxin or can be a silencing gene. So you do something to those neurons during this window of opportunity so that now you can, according to what gene you put here, so now that you can manipulate them. And so, based on this principle, and based on depending what gene you can put here, I will give you now an example of a gene that has proven very useful to, instead of a color gene, instead of simply coloring these genes, now I put a gene that I make the neuron to express in this window of opportunity, that typically is 1 day. And then later on, that neuron synthesizes that protein, and this protein now allows me to do something to the neuron, for instance, to reactivate it. And how can I reactivate a neuron? I can use these that are called optogenetic proteins. These are a recent addition to the toolbox of neurobiologists that are ion channels that are taken from some microorganism that are ion channels. So let ions flow and like ion channels in a neuron. However, these are light-responsive ion channels. So now these are proteins that in the dark do nothing. When you shine the light on them, rapidly on a millisecond time scale, like an action potential of a neuron, induce action potentials in that neuron. So it's a rapid way to use light of the right wavelength to modulate the currents of a neuron. So this is a gene. These can be inserted into neurons instead of this red gene. Instead of coloring the gene, now you can color them and put this during a window of opportunity. And now this gives a way at a later time point to reactivate them. So now the question is, can I use this to reactivate the memory? And this is what has been done 3 years ago by Susumu Tonegawa group in the States, who used optogenetics to induce a new memory and also to induce false memory. I will take you briefly through these experiments that use everything that I will told you so far. And then this is my one before the last experiment that I will tell you. So this is Susumu Tonegawa on a visit when he visited Rita Levi-Montalcini. He is an interesting guy because in the 80s, he won the Nobel Prize for immunology. He was the one who discovered how antibodies are made in the body to fight viruses. So he was an immunologist. And then after he got this award, he decided he would study the brain. And he has done some very important contributions in the study of the brain, amongst which these experiments that I told you. So he used this tool, and he used a very simple behavioral experiment. This context conditioning. You take a mouse, you put him in a blue spatial context, and then you put him back there, and he is used to this context. When you put him in the blue context, in Sala Azzurra, you give him a small shock, then he remembers the shock. And so when he is put back there without the shock, he will have a freezing response. You can very easily measure it. He will not move. He knows that something is happening. So he remembers the shock. If he's put in a similar context, he has no fear. So this is a very simple test. We know exactly which brain area is responsible. So you know which cells you want to label. And so he used this, and he used, again, the experiment is the following. He puts the animal in the blue context, context A. He shines light because this mouse has the channel, the optogenetic probe to genetically label his neurons that are active. Here you have the doxycycline, so the drug, so that the neurons are not labeled. He gets habituated to that context. Then you remove the drug. So you open the window of opportunity. You let here in a different context, context B. And then you give a foot shock here. So here he is labeling neurons, these neurons, whose activation is associated with the expression of this optogenetic probe. Then he puts them back here in the same context that was non-fearful for him. And then at some point afterwards, he keeps them. He has a light that is shining a light on those neurons with a small optic probe. And what you see is really dramatic. What you see is the following. You measure here the amount of time that the mouse has a freezing response. In this phase here, when he should not freeze because he was habituated. And when you do not shine the light, he does not freeze like the control. You shine the light for 3 minutes, this is how he freezes. You turn the light off, he doesn't freeze. And you can make this even greater. And you have all sorts of controls that you can show that this is very specific and this and that. So this was the first formal proof that instead of correlating the activity of a certain group of neurons, you actually causally prove that the activation of those neurons that were labeled activated during the learning phase when he received the shock, you can reactivate them afterwards, not putting them in the context B, but activating the cells that were labeled in context B. So you are downstream, and you are keeping them in a context that was neutral for them. You can play this to do also to create a false memory. And this is, I'm coming to an end. And this is, you put them in without, the window of opportunity, you give no shock here, but you put them in the red context. So these will make will synthesize the optogenetic probe that corresponds to this spatial context. Then you put them in the context B, so those neurons that are the gray neurons are activated, which are different from these. But these do not make channel rhodopsin because you are on doxycycline. And you give the shock here. So the mouse thinks that the shock is associated with the red neurons. And so when you put him back on the red context, he freezes now. Instead, he had received no shock there. So this is what is called the false memory. That is a very simple example of how you can trick the memory system by playing with the neurons that were activated during a certain window of training. Now, final few minutes. You can tell me, okay, so initially you told me about how important synapses are. Now you show us recent experiments in which you reactivate neurons, whole neurons. But you can say, you told me that a neuron has thousands of synapses and he can activate only certain of his synapses. So this is now the next frontier. The spatial scale of technologies that allow the reactivation of neurons are at the scale of the whole neuron. So you can reactivate a whole neuron. The next question is, because now the question is, I can reactivate this synapse and not this one in the real neuron. Can I do the same experiments as I did before by genetically tagging not the whole neuron, as I told you so far, but genetically tagging this synapse and not this synapse? That's the current question on the floor. And so,
in terms of scale, what does that mean?
So, in terms of scale, let me give you the answer at two levels. This means that the scale of a neuron typically is hundreds of microns, and this is a fraction of microns. So the scale of a neuron is on the millimeter scale, let's say, and the scale of the synapses is on the micron, submicron scale. And in terms of relative scale, this means that is one of thousands of synapses that this neuron contains. So there is also in relative terms is, can I tag a very small portion of a neuron to ask now an important question, that is, the engram is a cell, a neuron, or a combination of its synapses? I told you about cell assemblies, and this is how I can depict. The engram, in my cartoon, I had combinations of neurons that are all red because they would contain the trace. But everything that the synaptic plasticity told us is, I don't know if you can see, this is, the red dots are the small dots of a neuron, so what I call synaptic engram. So the engram is a set of synapses on active neurons. To address this question, that is the question now on the floor, you need, the current engram technologies have a cell-wide spatial resolution. Now you need new experimental tools to reduce the spatial resolution of engram technology down to the synaptic level. As Ricardo was asking, this is a great order of, many different orders of magnitude of scale. So this is depicted here. You want to be able to express that optogenetic probe that was expressed at the whole neuron level, and you want to shine light only in a combination, in a subset of its neurons. So how can I make an RNA in response to a synaptic activation that normally is done as in the previous technologies at the level of from DNA in the soma, in the cell body? How can I make engineer it to make a protein only locally? Well, you have the answer because I told it to you 20 slides ago. There is local protein synthesis. So now, instead of using what we have done, we use a physiological synapses, physiologically translate mRNAs following the induction of potentiation. And these mRNAs are usually repressed, translationally repressed, and travel in the whole neuron. And then it is synaptic activity that makes that RNA to make protein locally at the scale of the synapse. So we exploit this normal mechanism of synaptic plasticity to express a reporter protein at potentiated synapses. And this is a very brilliant student at Scuola Normale who did this work, and he just discussed his PhD thesis. I will take you briefly to what he did. So here you see that colored, you see that normally you would activate the expression of the gene in the whole neuron, but with the concept that he made, with a few very clever tricks, you see the yellow spot only at a very small subset of its synapses that in the culture were activated. So this is we can now make an optogenetic protein only in a few synapses of that neuron, and we can show that, for instance, if you use here a probe that activates, that is a marker for that synapse being activated, and now the reporter protein that we express is expressed in coincidence with this. This is the same neuron with two different colors, and you see that only the green synapses are also red. And so this is a control to show that you can express that protein only here, and there is a very, very nice correlation. The crucial experiment is the following. We use, and then I will take you to an end. You use what is called glutamate uncaging and two-photon microscopy. You can take the neurotransmitter in a chemically masked form that is inactive. And so you bath the neurons with this chemical transmitter that is not acting on its synapses. Then, with a two-photon microscope, you shine a light in a very small spot of a nanometer scale, and tens of nanometer scales, and you activate, and this two-photon microscope uncages the glutamate, making it active. So now this is a way for locally stimulating this synapse, but not the neighboring ones. And we can show that, here you see, this small white spot is our optogenetic probe that is being made into protein in response to the local activation of glutamate and not in the neighboring synapses. So this now is a tool, and we can map potentiated synapses in memory tasks in vivo. We are doing this. I won't take you. So this is now the current spatial limit of the engram technology. So now the question is, we are repeating Tonegawa experiments at the synaptic spatial resolution. So now, instead of reactivating a combination of neurons, we are reactivating a combination of synapses in active neurons and asking the question, can we interfere with the memory, or can we, for the necessity question, or can we reactivate the memory? And the interesting point is that we can do this in a normal mouse or in a mouse that has signs of Alzheimer's. So, to conclude, I believe that what I told you, I tried to take you where these memory studies are, where is the frontier of these memory studies, where the techniques to study the engrams are taking us, and hopefully this might fill the gap between, that I told you in the beginning, between Alzheimer's disease and memory mechanism. And I thank you for your attention very much.
Thank you very much, Antonino. Are there questions?
Far from colliders.
If your experiment will be successful, right? I mean, for consistency with what you said before, the answer will have to be yes or not.
The answer is, if the answer is going to be yes,
yes,
the synaptic plasticity paradigm will hold true. If the answer will be no, there might be either technical reasons, or pending these, or it might be that it is true that synapses can be potentiated independently, but that there may be limits to the synapse specificity, which is discussed in the literature. For instance, one thing that we did measure is something that theoretical studies much needed. In a neuron, how are the activated synapses geometrically localized? Is there a higher probability for an activated synapse to be close to another activated synapse in vivo, or is it random? Because now with this tool we can measure this, and so we find that there is something that is called clustered plasticity, that activated synapses can tend to be clustered together, which is considered to be a limit to the synaptic plasticity level. So our technique, if the outcome will be a full yes, it will prove through the synaptic plasticity paradigm. That is an experimental paradigm, is a line of thinking. It is a way to test that thing, basically, yes.
What is the time scale between the activation of the synapses and the production of the protein?
A few hours. And so this poses the need, as I alluded before, so because the signals have to travel from the synapse to the nucleus and back, and according to the typical transport velocity rates and all these things, it's a few hours, depending also on the distance from the. So it's a scale is a few hours. This means that there must be a tag at the potentiated synapses that is a sort of self-reinforcing molecular memory that lasts for a few hours, and this can be measured, and you can measure that there are these tags that last for a few hours. So this is very consistent. So basically, the mechanism is in two steps. Whilst the signal travels to the nucleus and back, you have to keep going that synapse with a transient protein synthesis independent tag.
Thank you very much. Excellent presentation. You referred to two-photon microscopy. You said shining. Do you mean two-photon spectroscopy?
So
microscopy.
This is erroneously. I shouldn't have. It's erroneously. You shine laser light with two-photon excitation, and so it is not. We call it microscopy, but okay, sorry. I apologize.
Okay, and what
point taken? In jargon, we call this like this, but
to answer my understanding, the answer to your question absolutely is yes. And I think that for enhancement of the phenomenon that you try to do with two-photon excitation, also you can use the magnetic nanoparticles.
I'll wait.
As you said, yes. If there is technology to do that, and you answered your question, yes. I think that there are many available technologies to to help you to reach the same target, and one of them should be, my understanding, application of the magnetic nanoparticles and to do the activation that you are looking for.
Certainly there are many different ways to locally activate the processes, but to my understanding, to my understanding, the spatial scale and the time resolution at which magnetic focusing can be used is not high enough for the spatial scale that I need. Because you need to focus the activation on the scale of a synapse. But I'm happy to learn different ways.
If you apply the magnetic field, you can excite this magnetic nanoparticle. It is the fastest process in the nature.
Yes, but spatially, how can you focus? What is the spatial scale of that focusing? Because I understand you can activate you need for this type of experiment also a very precise spatial scale. So the question is, can I activate the magnetic field
especially
focally?
A nanoparticle? Yes.
Focally.
The answer is yes.
But the nanoparticle is spatially. But okay. Anyway, we can. I'm happy to hear what you think about.
One more thing. When I was young, I had a book from Cengiz Aytmatov from Uzbekistan. He referred to process that the old people in Uzbekistan they did to create the false memory. They were able to do that, and they gave also the somehow wrong information to people when they did these experiments, and they succeeded. And the people, they forgot what they had in their memory, and they were able to delete and give the false information to them, and it worked.
Yeah, I mean, the point of in the psychology literature, the issue of false memory is a very precisely measured phenomenon, and so what is being done now is that you can start.
It was not psychology test. It was they used the pressure and temperature. They applied on the brain physically. They changed the pressure.
Okay, no, I understand what you're saying. Yeah.
Yes.
Okay. Physical process. Okay.
Physical process.
Yes,
what they did. Yes. Thank you very much.
Okay.
Are there other questions? Tonino, how fast is the technological progress in your field? I mean, it's because you now can do very precise experiments that probably were not doable 5 years ago.
Yes, certainly so it is difficult to give a measure. Progress is very fast. I think that what has been really fast in the past 2 decades is the combination of biophysical techniques with genetic techniques. Neurosciences was until the 2000s were mostly the realm of electrical signaling. So the biophysics of electrical signaling really dominated also our thinking of how the brain works and how neurons and synapses work. Molecular biology, whose boom was in the 80s with recombinant DNA and all that field, merged with this around in the late 90s as on massive terms, and so this created a real. Now we can combine genetic techniques with biophysical techniques. And so I think I don't have a measure for how fast. You certainly have more precise parameters of how in your field, but it is fast, and competition is fast.
Very good. So we can thank again Professor Cattaneo. I leave the stage to Franco, who will introduce us to the exhibition that has been prepared and will say a few words about the Scuola.
Okay. I've just been charged of reading this introduction. It was prepared by Alberto Lusiani, who supervised the organization of the exhibition. So I'm just a reader here, right? Just an introduction of what Scuola Normale is, a little bit of history and what is in the exhibition. So the Scuola Normale was founded in 1810 by a Napoleonic decree which dealt with places of public instruction in Tuscany, which was part of the French Empire since 1807, and referred to as the departments of Arno, Ombrone, and Mediterraneo in the terminology used in revolutionary France at the time. Scuola Normale was a subsidiary of École Normale Supérieure in Paris, and was granting 25 publicly funded places for students in the humanities and sciences. So in 1811, 25 students were selected for the first time. However, the Scuola began operating only in 1813, only for 1 year, because in April 1814, Napoleon was forced to abdicate. The term Normale refers to the mission of the school, which was to train middle and high school teachers able to convey norms in a context where training teachers was connected to forming citizens loyal to the laws and the emperor. Scuola Normale and École Normale did not initially have the denomination Superiore or Superiore. In France, after the institution of the École Normale Primaire in 1845, the school was denominated École Normale Supérieure. So it was a distinction, primary school and high schools. This was for high schools. In 1846, the Grand Duke of Tuscany, Leopold III, established a Scuola Normale Toscana, also called the Scuola Normale of the Imperial Reign, as it was then connected to the theoretical and practical Austro-Hungarian system designed to train teachers and masters for secondary schools. After the Italian unification, the Scuola Normale of the Kingdom of Italy was formally established in 1862. And in 1967, the Italian Republic denominated the school Scuola Normale Superiore of university and doctorate level studies. So, Scuola Normale keeps an archive of its documents, and some documentation on the admission process and on the admitted students has been systematically archived since 1857. Since 1884, the candidates' written tests have also been archived systematically. Also, during time, the Scuola Normale archive has acquired a considerable number of document collections through donations. One example of such donations is the archive of the Salviati family. I think it's the one that you can see here, which keeps the records of the various commercial activities of this family from the 12th century to the 20th century. So this is really a huge archive. So you can see that it's very old, right? The photo exhibition contains a reproduction of a selection of documents from the Scuola Normale archive. And in particular, it contains samples of the admission tests, the question and answers from the admission tests from 1918 to 2002. The idea is to show how the admission tests changed over time. And the opportunity is taken to show samples of the answers of the tests of some notable students, like Enrico Fermi. That one is really notable. Carlo Rubbia, Gilberto Bernardini, who was also director of Scuola Normale from 1964 to 1977, of Massimo D'Alema, who was Prime Minister in Italy from 1998 to 2000, and also of Alessio Figalli, who's now very famous and because he got a Fields Medal in mathematics 1 month ago. We present posters with additional pictures, information, and a few anecdotes on Fermi, Rubbia, and Figalli. And finally, we present a selection of old photographs of students, professors, and some college structures. The oldest picture in the exhibition is dated about 1870. The reproduction and posters and the digitizations have been specifically made for the exhibition, which has been prepared under the supervision of Alberto Lusiani, who apologizes for not being able to attend because he has a conference in Germany and he has to be there today, so he apologizes for not being here. Who is a physics researcher here at the Scuola, and also with a collaboration of Maddalena Taglioli, who is head archivist of the Scuola Normale, and who has an extensive knowledge of the archived material and highly appreciated experience and dedication in preparing exhibitions. And also Chiara Visentin, a very young collaboration who we want to thank, because he's a very young collaborator of the VIS program, which is a program which means virtual immersion in science, and it is a program of the Scuola Normale for outreach and scientific dissemination. VIS is headed by Professor Andrea Ferrara and coordinated by Marcos Valdés, physics researcher, and the VIS area is coordinated by Professor Luigi Rolandi, and includes several activities, one of which is a series of thematic tours organized in cooperation with the archive and the library of the Scuola. I think that there are some other acknowledgements, but I will not read them. One of them is to myself, so I won't read that. And then, okay, so please enjoy the exhibition, because that's the important thing. If you want, we can put this on the website.